Good afternoon, everyone. Welcome to Quantum Day. My name is John Gibson. I'm the director of the Center for Electronic and Computer Music in the Jacobs School. And we're very excited to host you all and all of you people who are remote with us. I wanted to say a few things about our Center for Electronic and Computer Music, especially so people here know about it. We are mainly a bunch of composers who are interested in doing things with electricity. We do all kinds of different things, and some of those things you'll be seeing here as I'm talking. We're really focused on making music and giving performances in new and innovative ways. But we also have a history with computation in music. In 1966, the composer Yanis Xenakis came here to IU and taught here for 6 years before he went back to Paris. And the IU Press published the second edition of his book, Formalized Music, which was, if you've ever seen that before, it's one of the earlier sort of expositions of how you might think of probability and statistics in the course of generating music in lots of different ways. It was quite influential in our field. And so we were very happy to have a bit of that heritage with us. And so we often do try to think of ways to imagine how computing could help feed into our music. So we do a couple different things. We have musicians who are maybe a little more intuitive, and they like to just sort of imagine what sounds are going to work for them and how to make the music flow. But we also have people who are interested in doing kind of wacky things with numbers and sound. One of them is in this room with his advanced sartorial sense. You'll hear from him later. So he's really interested in sonification and all kinds of other things. I remember one of my first encounters with computation in music when I was developing this piece. It was supposed to be about Schumann, the classical composer. So I was supposed to take some music of his, and I wanted to weave that in and out of my own little weird electronic music world. And so I developed an algorithm to kind of take the music that he wrote and sort of deconstruct it and reassemble it probabilistically. I can't even say that because I'm a musician. And so I did that because I can code. And it was like magical. It was like the first time I thought, wow, this doesn't have to be apart from my musicality. It can be a part of my musicality and actually enhance it. So one of the things we're really interested in doing is kind of harnessing computational approaches so that we can integrate that into our musicianship, not have it be sort of separate, but have it be a way of taking us out of maybe our sort of boundaries that we create for ourselves musically and discover other things that we can do with sound and music. It's really a valuable thing for anybody, no matter what kind of genre of music you're interested in. So I think they already said the end, right? The picture? I didn't pay attention to that. So I'm going to turn it over to Professor Baxter, who knows way more about quantum anything than I do. So please welcome Professor Baxter.
Thank you, John. So welcome all. My name is Dave Baxter. I'm the chair of physics here at IU, and I'm also the managing director of the Quantum Science and Engineering Center here on campus. And welcome to Quantum Day. I want to set a little bit of a context in there. First, I want to thank a bunch of people. I really want to thank John and the Center for Electronic and Computer Music for hosting this. I want to thank Adrian German and the Quantum Technologies for Everyone Club for doing so many of the logistics, and I really want to thank all of the guest speakers we've got who are, I think, going to put together a really interesting and varied program. So why are we doing something? What is Quantum Day? And there's a few of you in the audience that I think know a fair amount about this, but for those who don't, quantum mechanics is sort of the science of things that are very small. And as a result, it's the science that's behind most of modern technology. It basically controls all of chemistry. It allows us to understand how materials work. It allows us to make computers and things like green laser pointers and so forth. And we spent much of the 20th century figuring out how to harness those things and make useful things like green laser pointers and things that are even more useful than that. Within the last 30 years or so, we've realized that as weird and wonderful as quantum mechanics is, and how wonderful it is at making new technologies, there are aspects of quantum mechanics that are even weirder that we've been knowing are there for a while, but now we started in the last 30 years to figure out how we might actually be able to turn them into useful technologies that can transform the way we model things, transform the way we affect security and data, and all sorts of things. And much like the technology that goes in behind electronics and so forth, much of what we need in making this new technology come about doesn't need people who are understanding all of the details of quantum mechanics. We can't have a global technology worth trillions of dollars that relies strictly on physicists. That would be a really bad idea. But we need to have a bunch of people from a wide variety of fields who can bring their expertise to the things that we need to add into the physics to make things that are actually practical and to find new frontiers. And that's sort of the thing that's led to what's being called the second quantum revolution, and it's the sort of thing that was behind our thinking in founding the Quantum Science and Engineering Center here on campus. One of the things that we've specifically done over the last couple of years associated with that is we now have a new master's program that is sort of specifically designed to help onboard people into the quantum realm that don't come from a physics background, and start to bring in all of those people from those other branches of science and knowledge that are going to be very important for making the new technologies. And I gotta say that a day like this tells me that we've sort of gone beyond our wildest dreams. When we first started, I had no idea I would be having a session on this in the Jacob School. And I just think it's absolutely wonderful. And so with that, I will turn it over to the next, welcome you, thank you all for coming. And again, thank you to the speakers and to Adrian and the club. And I'm looking forward to seeing what's coming down the pipe.
Thank you, Professor Baxter. So I'm Arpan. I'm the president of Quantum Technologies for Everyone Club. I know it's a big name, but we have a cute acronym. See? So, thank you all for coming to our Quantum Day. This is the last event of our semester, and we wanted to go off with a bang. And I'm very pleased to introduce you. If you have gone through quantum computing, or if you have some experience in quantum computing, it's well and good. But if you have not, I'm very pleased to introduce you to Dr. John Donohue. He's the scientific manager at IQC. At IQC Waterloo, the Institute for Quantum Computing. And so this will be your first lesson in quantum computing if you have never gone through it, but it won't be scary, I promise you that. Okay, so with that, I give my best to Dr. Donohue, and I think he has started sharing his screen. So whenever you're ready.
All right, thank you. Can you hear me okay?
Yeah.
Perfect. All right. Thank you for having me today. Thank you for the invitation. It's great to be able to speak to you. And it's really great to see such a great crowd together, really at that intersection of music and quantum. I think that's a really interesting place, especially when we start talking about how we talk to people about quantum. So my name is John Donohue. I'm the Scientific Outreach Manager at the Institute for Quantum Computing. It's my mission to find different ways that we can teach people quantum mechanics and let them get some hands-on experience with it. So for the next 15 or so minutes, I'd like to talk about some hands-on activities that you can use to help teach people quantum mechanics. Some things that you might be able to replicate yourself, some things that are relatively cheap, some things that are not so relatively cheap, but hopefully things that you can potentially use to, if you're in a Quantum Technologies for Everyone group, for example, do love that acronym, by the way, that you can use to start engaging with audiences and bringing them into the quantum world. So just a bit about where I'm from. I'm at the Institute for Quantum Computing. We're a research institute at the University of Waterloo. So we were founded in 2002. We're just over 20 years old as an institute, as a collaboration between 7 different University of Waterloo departments. So when people think about quantum mechanics, the first thing they usually think about is physics. My background personally is in physics, but we wanted to make sure, of course, as quantum computing was becoming more of a topic of discussion, that we were bringing in the right people from many, many, many different disciplines. This includes things like computer science, chemistry, engineering, and many parts of mathematics. Of course, as the field has continued to grow, there are many other areas that become welcomed into the fold, including things like music that I don't think anyone 20 years ago would have even thought was possible. So it's really cool to see things like that happening. We do offer things like specialized master's and PhD degrees in quantum information. If you're interested, feel free to check out our website for details on that. But my particular goal is leading the outreach efforts at IQC. So how we talk to people about quantum mechanics, and we do that through a variety of means. Some of our big programs include summer schools at various levels. So we do run a summer school really focused on experimental quantum information processing. So this is how we try to bring in undergraduate students, give them in-person lab experience, working with some of these devices, working with things like entangled photon sources, NMR machines, all these things that you might not be able to get hands-on experience with otherwise. We run a similar program aimed at high school students, letting them get some experience and learning things that are just difficult to find in a high school curriculum, as well as one for teachers called Schrodinger's class, which is aimed at giving teachers lesson plans and ideas that they can introduce, so they can introduce quantum computing and quantum information to their students. We also have traveling museum exhibits, we'll host public talks, we'll have a presence at science fairs, all trying to find ways to engage different audiences and get them excited about quantum information technology. Of course, whenever we're trying to talk to people about quantum information technology, you have to understand that people are coming in from a variety of levels. So as outreach, we want to be looking at communicating to audiences that range all the way from young children and trying to get people on the street interested in quantum, all the way to high school teachers and high school students who are developing that technical background or helping people develop that technical background, all the way up to engaging with other academics. So how do we tell our story and how do we teach people what quantum means? Okay, essentially, how can we bring quantum to everyone? So that's kind of what I want to talk about in the next little bit, is some of the different hands-on ways that we try to accomplish that. This is a quick note. I know a lot of people today are going to be talking about coding. It's very cool. It's not what I'm going to be talking about today. Coding is, of course, a fantastic way to learn quantum mechanics. There are a ton of resources out there. I know I saw on the schedule there's going to be a few people talking about that later. But there are some people who do learn very specifically through hands-on approaches, and that's kind of what I'm going to focus on today. So firstly, when we're talking about young children and the general public, I think there are two big ways to really grab their attention when we're talking about quantum information science. And option number one is to go for big and whiz bang. We can show people pictures of chandeliers all we want. We can tell people about the quantum world all we want. But sometimes when you're dealing with younger children, you need something that really catches their eye very, very quickly and very, very efficiently. So a couple of key options there that are relatively accessible. If you're at a university that has access to liquid nitrogen, you can get your hands on some type 2 superconductors, some magnetic tracks, and build a superconducting levitating frame. So this is an effect called the Meissner effect. It is a quantum-based effect, and you can use that to tie in nicely to a discussion about how these superconducting circuits actually work, how we actually build quantum computers that are, of course, accessible via cloud interfaces and things like that. This one we found has a lot, gets kids very excited, very interested, and you have to be very careful they're not going to put their hand near the liquid nitrogen, but nonetheless, it's a great way to get them involved. So this one's relatively common. You see it a lot in quantum outreach activities. There are some other things that you can think about, though. So one of the things that kind of blows my mind about quantum physics, about the current state of experimental quantum mechanics, is that we can do things like trap individual atoms. We can actually use the technologies we've developed over the last few decades to isolate and address individual particles, individual atoms. And so what we developed was a live ion trapping experiment that we can travel around with and use to engage with both audiences, young and old. This development and how we've been able to control these systems is astounding. I think something that a lot of people are not aware of. So what we did was we developed a analog version of this, of the technology used to trap ions. So it's something called a quadrupole ion trap. Now, of course, if you want to trap individual atoms, you need to be doing this under incredibly high vacuum, so that's not going to travel around particularly well. But if we're looking to trap something a little bit larger, a little less sensitive, in our case, what we're trapping is charged spores of lycopodium powder, so essentially protein powder of sorts. We can do that in open air in a fairly robust set that we can travel around with. So this is a set that we have used with high school students, undergraduates, general VIP tours, but over the last term, we've also been using it to interact with elementary school students from around the region, bringing in a few hundred elementary school students over the past few weeks to learn about ion trapping and how some of these quantum technologies are developed. So these kind of whiz-bang things can really open the imagination of younger children and audiences and get them interested in this technology. But if we want to get them a little bit more hands-on involvement, it's helpful to have some kind of activity that they can actually participate in more directly, and ideally do some kind of work with that. Now, of course, we're dealing with quantum technologies, unless we're talking about cloud access machines. That can be quite difficult. There's a lot of expertise that goes into developing these technologies, but we can still really get at some of the underlying principles quite efficiently. So for one example, if we want to start talking about interference with students, we can do things that are very analogous to the double slit experiment, but using classical laser pointers and doing things like measuring the width of our hair. If we shine a laser beam across a hair, light will go one side around the hair, around the other side of the hair, and as it diffracts around that hair, we'll see a familiar interference pattern, very analogous to the double slit or single slit experiments. If we measure that interference pattern, we can actually determine the width of our hair, which is something, of course, that we really can't do with the naked eye or rulers unless we really have a decent microscope. Okay? So this is a way that we can start talking about things like interference, that we can start talking about things like quantum sensing technologies, all with an accessible experiment where the mathematics are very accessible to middle school students and above. You can also look at things that are even more arts, so tending towards the visual arts. So polarization is a degree of freedom that we often use in encoding qubits. This is especially used in things like quantum communication, but also useful in various photonic quantum computing platforms. Now, polarization is something that students in upper high school do learn about, but not something that's incredibly unapproachable for younger students, especially if we give them something fun to build. So one of our favorites to do is something called birefringence art. We look at things that rotate the polarization of light. So if you have two cross polarizers, as you can see in this video here, they kind of block out the screen. But if you introduce something that rotates the polarization of light, it will A, allow some light through where there shouldn't be light that's allowed through, and B, using the right brand of tape, you have to do a little bit of experimentation to find the right brand. You can get these kind of colorful patterns to pop out as the light rotates its polarization through the tape. We were also able to kind of put a projector in place so they could magnify their art and make it really large if you want to make a show at a science fair, for example. But this is a great way to get younger audiences involved and also a great way to connect older audiences and to start talking about technologies like quantum key distribution and photonic quantum computing. This is really the same ideas that underlie it. Okay, so that's how we can kind of just talk to general people, anyone who maybe has never heard of quantum before in their life, maybe is not necessarily set up to really want to care about quantum. How can we bring them in and show them things like that? But our bread and butter here really is high school students. If you have the opportunity to chat with a high school class or high school teachers, they are more set up to potentially encounter this material. But of course, high school classes are very, very tight on time. They don't always have the time to kind of work in this material or the expertise to work it in delicately. So for example, this varies a lot from state to state, province to province. In the Ontario curriculum, there is, of course, grade 12 physics, and that does include quantum mechanics in it. So some of the topics included there do include things like the photoelectric effect, like the Compton effect, like emission spectra, like wave-particle duality. But a lot of what they talk about is from what we might call a classical quantum lens, kind of quantum from the 1920s, let's say, as opposed to our understanding of quantum mechanics today. So if you do have an opportunity to talk to high school classrooms, I highly recommend taking a peek at whatever curriculum they are teaching, seeing where you can connect, because that's always the important thing. It's going to be very difficult to work something into a classroom that comes completely out of left field, but if you can find the connections between what they're already learning about and what you want to teach them, that makes it much easier to A, convince a teacher to take the time, and B, connect to what they already know. So in developing this, we've developed a workshop that we call Schrodinger's Class. This is a weekend workshop for high school physics educators. We've held it annually since 2015. Importantly, the materials that we use were not just thought up by a bunch of academics, they were developed in collaboration with educators. And we've been very lucky to be able to cover costs for our participants because as you can imagine, teachers don't always have a big travel fund that they can access to attend workshops like this. Okay, and like I said, the key lesson for this is that we want to ensure that materials that we develop are connected to both quantum technology and to existing topics in the curriculum. So for example, if we want to talk about QuTE, similar to the biofringes are, we want to get one step higher because we're talking to high school students now. We want to connect to a familiar concept to them. In this case, we connect to the polarization of light. And what we want to do is we want to introduce one new idea. And that new idea is the fact that you can measure the polarization of a single photon in multiple measurement bases. Effectively, in quantum mechanics, there's more than one way to measure a quantum state. We build this always with an application in mind. In this case, the application is quantum cryptography. This gives them A, a way that they can connect it to what they're already learning, and B, an application they can build towards to make it seem at least like it's going to do something useful, not like it's something we're learning for no reason. But we only introduce very little new ideas in trying to build up this technology and build up these lessons. Of course, there's a lot that goes on in there within that new idea, but that also is a new idea that does extend all across quantum information technology. The idea of measuring different bases is not just useful in quantum cryptography. Another example, one familiar concept to many students who do learn some quantum mechanics at the high school level is wave-particle duality. So we introduced one new idea to them, which is the idea of Mach-Zehnder interferometers, in particular, what happens to a photon in a Mach-Zehnder interferometer. And then we can build that up to applications in quantum computing. You can think about some very, very basic 1-qubit quantum algorithms like the Deutsch-Joseph algorithm, and think about them in terms of Mach-Zehnder interferometers. So we can use this to build up to applications in quantum computing, all through introducing just one little twist on something they're already familiar with, and hopefully teach them some of the ideas, some of the important key factors of quantum computing that give it that advantage and what make it different than classical computing. Okay. In addition, we do try to have a bunch of hands-on activities. So some of these are things like measuring the uncertainty principle and the width of your hair with laser pointers, thinking about measuring Planck's constant with LEDs, experiments with quantum dots, thinking about 3D movies and how those connect to polarization. So these sorts of activities are very affordable for the classroom, which is very important, but not particularly quantum information centric. They maybe get at some of the ideas of quantum mechanics or some of the underlying concepts that connect to quantum information, but not quantum information centric in themselves. Now, if you want to get really keen on the quantum information aspect, you can do things like there's a bunch of pen and paper activities or kind of group activities. One example we like is a coin flipping activity that mimics quantum key distribution. Now, this allows students to kind of role play in different Alice, Bob, Eve roles, kind of letting the rules of quantum mechanics be embodied by what happens to coins in different boxes. And this is affordable, of course, it's just coins and boxes, and very quantum information centric. But of course, whenever we have these kind of role-play games, they are a little bit contrived. We also do have some build-it-yourself demonstrations on quantum key distribution using lasers, where really the only cheat we're using is that we're not using single photon sources. These are quantum information centric and very close to real, but can be quite expensive. Okay. Of course, this is assuming that we're trying to build things for teachers to use for their students. But what if we could instead bring those students to us? We could bring them to a center that has expertise in quantum information science and give them some activities to do. So that's the idea behind our quantum school for young students. This is a 9-day summer school that we run every year for students in grade 11, 12. We've been hosted annually since 2008, this particular one. And here, because we're able to bring in kind of students who are academically very strong, we're able to get into some incredibly deep concepts with them over the course of it. So we do assume that they come in knowing a little bit about linear algebra. They know, the basics of vectors and matrix mathematics. We do provide them a primer text in advance for them to study those concepts if they maybe haven't learned them officially in class yet. But we start off by going over those concepts with them, as well as peppering in some of the historical context of quantum mechanics. We also teach them full Brockett notation in this course. We then connect those two by talking about what superposition and measurement really mean, by also focusing on a variety of quantum systems, showing how they look very different, things like polarization, path-based interferometers, and quantum spin, but they all follow the exact same principles and you can model them using the same toolbox. We then break out and use quantum key distribution as our first key application. It's a very simple application to talk about with students. You only need to know that we can measure things in different bases, and that's something we should be getting across very early. And then from there, we can kind of web out into talking about many, many, many different kinds of applications, many, many, many different kinds of topics, including entanglement, Bell's inequality, quantum computing, different quantum algorithms, quantum teleportation, specific implementations, even things like quantum error correction get addressed in this course, and the high school students do tend to appreciate seeing some of those more advanced topics. Throughout this, we have opportunities for students to work with other people, problem sets, social activities, and very importantly, lots of hands-on lab experiences. So I do see, I just want to quickly run through this before, you see the clock is ticking a little bit. Some of those labs are very focused on the quantum fundamentals. So these are things that are perhaps overlapping with things that are commonly taught in schools, things like atomic spectra, things like sound resonance, and how we can relate that to how we build atomic clocks, the fraction, the uncertainty principle. If we go up one level, we can talk about things that are components in quantum information tools. So things like superconducting limitation, designing circuits, building gates out of polarization cube for polarization qubits, building interferometers. So not necessarily the quantum information itself, but very important components to building these devices. And then finally, we also do have been lucky enough to be able to afford some resources to really teach them some quantum information very directly. So things like quantum key distribution, having them work with real NMR machines, having them trap these charged particles, and also having them work with an entangled photon source to violate Bell's inequalities. And that is one of the tricky bits about getting some hands-on experience. So of course, coding pen and paper stuff can get very, very, very relevant to quantum information, but without that, and with a hands-on interaction in a bit of a different way. If we want to get hands-on experience with real equipment, there's a kind of this is a very, the axes on this graph are, let's say, very arbitrary, but just roughly putting relevance to quantum information versus cost, there's a pretty clear dependence that the things that are more relevant to quantum information cost a lot to develop. So what we're hoping to do is try to take some of these and make them low cost. In particular, QKD demos we found from feedback from our high school student and teacher participants get very high reviews in terms of helping them understand some of these materials. So one thing we've been working on is bringing these QKD demo costs down from a large, expensive setup that Thor Labs will sell you for $2,500 USD, something you can 3D print at home for about $150 USD when you include all the components. Okay, so that's kind of a broad overview of some different ways that you can engage with students, depending on what level they're at, depending on what resources you have available. If you do have a request for any materials, do feel free to email me. I'm always happy to kind of share some of the ways we build some of this stuff. And I hope you have a very happy World Quantum Day, and thank you so much for inviting me today.
Hello, my name is Micah Robertson. I'm the treasurer at the Quantum Computing Club at IU. It's my pleasure to introduce Walker Smith. Along the same lines of educating youth and getting them engaged, Walker Smith I think is a pro at this time. He's presenting this beautiful show called the Sound of Molecules as Roy G. Biv. I love the outfit, and he's done it at many different countries and been doing a bunch of shows all around the U.S. itself, and it's been really great. So it's my pleasure to introduce him. Thank you.
Yes. Okay, no feedback. Great. I don't think so. Okay. I'll just stand away from my computer speakers. Let's see. There we go. All right. Thank you for the introduction. Today I'm really excited to share with you my work with the Sound of Molecules show and thinking about how we can listen to the molecular world or the quantum world. So I hope today to answer three main questions. The first being, who am I? The second, what do atoms and molecules sound like? And why should we care? I guess there's 4 questions actually. So as Micah said, my name is Walker Smith, but you can call me Roy. And I actually just graduated from IU with degrees in chemistry and music composition from the Jacob School, working in the Center for Electronic and Computer Music, which you heard a little bit about. And both of these fields involve combining existing elements to make something new. In chemistry, those elements are, well, literally elements that you're combining to make new molecules and new materials. But composers kind of do the same thing, but their elements are sounds, chords, rhythms that we combine to make new songs. So I wondered, what was at the intersection of these areas? Could I make music using chemistry, or could I use music to communicate ideas in chemistry? And so my research background in chemistry was as a synthetic organic chemist, so the thing that like everyone who has to take a chemistry class complains about. And I got to see this machine a lot. I became very good friends with this machine. So this is a nuclear magnetic resonance spectrometer, which is actually the same technology as MRI that you might have in a hospital. And an MRI, lets us look into the brain and see like the inner structure of the brain. NMR kind of does that, but for molecules. So when you put a molecular sample into an NMR machine, you get out a spectrum. So each of these peaks corresponds to a different type of atom in the molecule. So you're sort of looking inside the molecule and seeing its structure and where the atoms are. But stepping back from this distribution is really, in a more abstract sense, it's a distribution of frequencies with different intensities, so the frequencies at which these different atoms in the molecule oscillate. And that made me think about a connection to music, because we can also represent sound as a distribution of frequencies with different intensities, or in musical terms we might call frequency pitch and intensity amplitude or volume. So what you're looking at here is called the free induction decay, so that's really not important, but the important thing is this is the time domain waveform that you get when you put your sample in the NMR machine. This is the raw data that the computer then transforms into that spectrum you saw on the last slide. The important thing though is that we can turn this into an audio waveform. So what you're actually looking at here is not this data in a chemistry software, but you're actually looking at an MP3 file that is the sound of a molecule. So let's hear an actual sound of a molecule. So this molecule is called Hippolyte J. It's a very interesting molecule that the research group I worked in was interested in finding a way to synthesize. I had the privilege of working with a great graduate student. His name was Rinyu Guo, and he found a really amazing way to make this very complex molecule from scratch. If you want to try making it yourself, here's how he did it. So yeah, it's a really cool molecule, so I wondered what it might sound like. So let's hear the sound of the nuclear magnetic resonance of Hippolyte J. Did you miss it? Here it is again. Oh, wait, sorry. There we go, okay. Nope. Okay. There we go, okay. Well, so that's what 3 years of chemistry research sounds like. So basically the little clink that you heard the first time is the NMR data being played out as an MP3 file. But we could slow it down to hear more of the details. So that was it slowed down by a factor of 10, and we can listen to different molecules and they sound slightly different. So all these molecules sound slightly different because of their slightly different structures. So before we look further into this, let's ask the question, why would you want to turn molecules into sounds? So the underlying idea here is something called data sonification, which is representing scientific data, or any sort of data really, through sound instead of traditional data visualization that we normally think of how we could experience data. And using sound as another dimension to appreciate data has a number of important applications. One of the most important being accessibility of data to people who can't see or can't see well. But even for people who can see, auditory representations can supplement or enhance our ability to understand data and student engagement as well by providing an extra dimension of sensory perception. And in this avenue, I've been really interested in developing this as a public science outreach tool through musical performances and as a STEAM, or you might have heard of STEM plus arts, educational tool. So today I'll be sharing this work that I've done with the Sound of Molecules performance, and then also showing a little bit about the interactive musical periodic table that I developed. So the first, my first implementation of this work was in December 2021 in a concert here at the Center for Electronic and Computer Music. We have 2 concerts, one in the fall and one in the spring. This was on the fall concert, and it was called The Sound of Molecules, where I appeared as Maestro Molecules to take the audience on a sonic tour of the molecular world. And I'll play some quick excerpts of the show, but the full recording, if you look up Sound of Molecules or my YouTube channel, The Chemistry Shack, you can see the full recording. But let's let Maestro take us into the molecular world. So he's gonna expand on those little molecular bell sounds we heard earlier. So take it away, Maestro. In order to hear all of the details of these sounds, we need to zoom in. So I'd invite you to join me as we shrink down to the size of an atom and listen to these molecules up close. Now we've entered the molecules world. Let's hear that sound again, but up close. At this level, we can hear all the nuances of the sound as it decays. So here's another excerpt from a little bit later in the piece where I took that sound and applied some electronic music techniques to manipulate it to create the, to represent the sound of an electron buzzing around the nucleus. As we get super close to these molecules, we can even hear the buzz of the electrons whizzing around the nucleus. So that performance was a really great experience for me because I was able to combine this scientific idea of data sonification with a more creative musical composition component. So sharing the sounds and doing sort of like a lecture for the audience with this character, but then serving as the molecular tour guide and actually taking the audience in deeper. And so at this point, I was very fortunate to receive several grants to develop a longer version of the performance at Wonder Lab Museum, which is a science museum here in Bloomington. And it was at this point that I came up with this Roy G. Biv character, because I wanted to answer the question, what does light sound like? So light and sound waves are fundamentally different types of waves, and also fundamentally different frequency ranges. And there isn't a scientific device that allows you to to convert electromagnetic waves of light into sound waves. So I had to invent my own. So this is the Light Soundinator 3000. I have this with me. So I'm going to demonstrate this really quickly. I'm going to put the microphone down, and hopefully the people on Zoom can still hear me. Wonderful. Okay. So, so this basically transforms the different colors, which are different frequencies of light, into musical notes, which are different frequencies of sound. So red is the lowest frequency, so it has the lowest pitch, and violet is the highest frequency. So if we go up the colors from red to violet, the frequency or pitch increases. Yay! So this tool allowed me to convert different colors into different musical pitches. And I applied this to chemistry because elements actually release light. So this is called a helium cathode ray tube, but it's the same technology as like a neon sign outside of a pizza place. So if you fill a tube with helium gas at a low pressure and pass an electric current through it, the electrons absorb that energy and they get excited and they fly around, but eventually they will relax back down to the lowest energy state called the ground state, and all that stored energy gets released as light, as this glowing purple color you see here. But the electrons aren't actually whizzing around all releasing purple light. In fact, this violet color isn't released by any of them, but rather, it's these sort of roughly 7 discrete lines that all blend together in our eyes into one coherent color. And each of these colors comes from different electron energy level transitions. So what do I mean by that? Well, let's say you have a basketball, and this is going to be our electron. So we give it some energy, we raise it up, then we drop it. Whee! So you might wonder why, so going back to that other slide, you might wonder why we only see 7 lines. I mean, what if we took the electron, couldn't the electron drop from anywhere? So we should see like the whole rainbow, and each one corresponding to all the different places we could drop the electron from. Well, so our electron or our basketball, it turns out in the quantum mechanical world, you can't just drop it from anywhere. You have to drop it from one of the floors of the quantum mechanical hotel. So floors 1, 2, 3, 4, or 5. You cannot, this is very important, you cannot drop it from floor 3.5. That is not a thing. The electrons cannot be there. And so these electron energy levels are quantized, which might sound familiar because that's sort of where the word quantum comes from. So these discrete quantized energy levels are what give us those discrete lines of light. So for example, if we drop all the way from the top floor, we release very high energy, high frequency blue light. But if we drop from like floor 2 down to the ground state, it's lower frequency red light. So with that in mind, here's the emission spectrum of helium again, and applying the sound mapping from the Light Soundinator 3000, let's hear all of these frequencies at once. So the helium chord. So it actually sounds pretty pleasant, in my opinion. And we can actually, the nice thing about treating it as sound is we can listen to these frequencies one by one, sort of as a melody. So let's see that. Yeah, so here's a musical notation, which entering college 4 years ago, I would not have imagined these two things being on the same slide, but here we go. So here we have the helium melody, or the helium scale. And when I was listening to this, I was like, this sounds really cool. It's really groovy. Like, what should I do with this? And then I'm sure the answer hit me, and I'm sure you guys, were thinking the same thing. Helium dance party. So this is my impression of what a bunch of helium atoms do when they're hanging out, releasing light. So this is an audiovisual composition, so you'll see the lines from helium flashing on the screen, synchronized to the note that corresponds to those frequencies. And I've moved them around in different octaves, so preserving the same frequency relationships, but different octaves, so you get like a bass sound, and then some chords, and then a nice little jazzy solo on top. So let's listen to an excerpt from the Helium Dance Party. Hold on to your seats. Thanks, helium. Now let's bring some other elements to the party. Hit it, hydrogen. So that's just a brief example of the helium dance party. For the full video, you can look it up on my YouTube channel, and there's a bunch of other elements joining the mix. And speaking of other elements and what they sound like, after doing this and making a composition with just a few, I wanted to look at other elements. So let's see, so since we're like sort of running a little behind on time, I'll just sort of run through this quickly. I basically developed an interactive software program that can allow you to select different elements and see their emission spectrum and also hear them. So we'll just play a few examples. So hydrogen, we already sort of heard. It only has 4 lines, so it makes a much simpler chord. But if we take something like oxygen, which has 180, it sounds very dense and complex. And a lot of the elements are sort of in between that, very dense, complex, and sort of more harmonious. So zinc is actually my favorite. It sounds very pretty. And it has comparatively few lines to the other metals around it, so I think that's why it sounds so nice. But let's listen to zinc. Very pretty. So I presented this work at the American Chemical Society Spring Conference a few weeks ago, and they actually put together a really great press release, which you can look up, titled "What Do the Elements Sound Like?" And this was like picked up like all over the country and like the world. It was super cool. So musical chemistry is becoming a thing. And I think just to sort of close, I think the coolest part about this experience for me has been sort of taking sonification of the molecular or quantum world and turning it into really personification. So bringing all of these things to life with characters and visuals, I think is what makes it, so great. And so this is a picture from a performance that I shared here in Bloomington to a group of 500 K through 8th grade students. And they just all loved it. I've never seen so many people, so many students like jumping up and down and dancing, ready to learn about chemistry. So I'd love to thank all the people who helped put together this work, and also the people who organized Quantum Day. Thank you very much. Is going to be, I'm going to introduce her. So we actually collaborated on this work together. Actually, could I show this slide really quick? Basically what we're going to hear next is the sound of a quantum computer. So moving beyond the sound of molecular systems. So David Drita is part of a research group here at Indiana University in the Iyengar lab, and they develop algorithms to map molecular dynamics, or the time evolution of a molecular system, onto a quantum computer and use quantum computers to solve molecular problems. So she's going to talk about the great state-of-the-art work they've been doing in that area, and then I will tie it back around to how we can hear the sound of a quantum computer, and then tying that all together at the end. So we can welcome David Drita.
Am I audible? Hello?
Hi, David. I don't think we can see your screen quite yet. We're still figuring that out.
Okay,
I
I'm
think
just
I need to
going to
unshare
share
my
my
screen.
screen. Yes.
Okay. Great, we can see it now.
Okay. Can you see the screen now?
Yes, we can see it.
Okay. Okay. So hi, I'm Devadrita, and today I'm going to be talking to you about how we can combine these three different fields, the field of chemistry, physics, and music all together in this very interesting fashion that Walker has already introduced to you. So I'm going to be talking mostly about how we can try to see what happens in a chemical reaction or what chemical systems do, and how we can try to study these chemical reactions on a quantum computer. And then Walker is going to walk you through how you can listen to what these chemical systems are doing, or what these molecules are doing that is being simulated on a quantum computer. So with that, let's start. So we as chemists are interested in all of these chemical reactions that form very important part of everything that's going on around us. So there are biological systems, atmospheric processes. There are everything involves a chemical reaction or a molecular system, right? So, and Walker talked to you about molecules, but they were static. But in these chemical reactions, there's a lot of bond breaking, bond making happening. So there's a lot of movement. So we want to understand how these molecular systems evolve in time. And then we want to basically extract out important chemical and physical properties from these simulations. So what we want to, so what happens is that these reactions that take place at a scale which is not accessible to our naked eyes, right? So what we want to do is we want to go into the virtual reality of these molecular systems. And I'm a chemist, but I'm a very lazy chemist. I'm a theorist. So, which means that I like to sit in the cozy, in my cozy office, in front of my laptop, and maybe just remotely log into a supercomputer or write up some code and try to see if I can build these or study the time evolution of these molecular systems on my personal computer or on a supercomputer. So here is just a snippet of how these simulations might look. This is just stolen from somewhere else, not my work. So let me just play this thing for you, where you can see how these atoms are moving in time. So this is a movie in time, and you can see that all the atoms and all the nuclei are being modeled as hard spheres in this particular simulation. So, but the problem is that, what creates a problem is that this is a very, it's a simplification of everything that happens actually. So what happens actually is that molecules, or the electrons and nuclei in a molecule, cannot be simply modeled always as these hard spheres or something like a ping pong ball. However, what they really are is that they are kind of these fuzzy ping pong balls. So instead of now having these nuclei or whatever atoms and molecules being these hard spheres, they actually have this this fuzzy distribution of being present at very different at different points in space at the same time. So there's a finite chance that we can find the particle anywhere in this fuzzy region. And what is more is that it can exist simultaneously at the center or at the edge at the same time. So that kind of makes the problem very hard for us, because now instead of just having one hard sphere for a particular atom or molecule, we probably have 10 or 100 number of these ping pong balls to deal with. So there is now an explosion in the number of configurations that we have to look into in order to really understand how the whole system is going to evolve in time, right? So that then creates this, demands this extreme amount of computational resources. So now when we want to treat or study bigger and bigger systems, the amount of computational time and storage increases exponentially. So which is now a problem for a PhD student like me who wants to finish a degree in 4 to 5 years, right? So I do not want to stay here for ages looking at this problem. So what we have here now is that we want to see if we can use a system that is equally fuzzy or equally mysterious or behaves in a strange way to simulate or to be able to model something like the chemical system. So that is when we turn to quantum bits or a quantum computer. So how does that work? So with the with the computers that we have, our personal computers or our supercomputers, they use bits as their information storage and processing unit. So each bit can either be 0 or 1, up or down at a particular time. So, but what happens with a quantum bit is that, much like our particles, which behave in a quantum mechanical fashion, the electrons and the nuclei, these quantum bits can also be in several different states at the same time. And what is more is that these quantum bits, or the states of these quantum bits, are what are used to store and process any kind of information. So basically, we are going to do any calculations or any computations using these states. And because they can exist in this in different states simultaneously, what we can do is we can also manipulate these states simultaneously, and that might provide us with an advantage in terms of the computational resources we require to do the problems. So then our way is therefore quantum computers. So now we want to be able to devise an algorithm that can be implemented on a quantum computer that exists today. So here is a brief overview of what our algorithm is. So we want to study a chemical system, and here is a prototypical example of a chemical system that we want to study. And on the other hand, we have something that is like the lattice of ions. And these ions are what are our quantum bits. So we are going to use the states of these ions as our information storage and processing units. And these ions can be manipulated using laser fields and magnetic fields. So if you see, these are our laser fields, and any interactions between any two ions are programmed using some laser fields. So this slide might have a lot of these equations, but you don't have to care about any of these equations here. What it essentially says is that we just want to be able to use the magnetic fields and laser fields of the lattice of ions to be able to simulate how this system evolves in time on this system. So essentially they are both quantum systems, but one of these systems is something that we can control externally. And so we want to be able to manipulate it in a way that from the way that this system evolves, we can see how our chemical system is evolving. So essentially we want to just make the two systems behave in the same way. And one such ion trap is at Phil Rishon's lab at IU Physics, and also at Sandia National Labs in New Mexico. And what I'm going to show you is a little bit of the results that we got from implementing our method on Sandia's ion trap. So when we use these laser fields and magnetic fields to see if we can simulate our chemical system on the ion trap. These are just two ions, Sandia's ion trap. And when we did that, what we found is that our theoretical results, which are these solid lines, were matched very well with the experimental results from Sandia's ion trap simulator. And what is more is that after we got these results from Sandia, we were able to take a step further, and we were able to do some kind of transformations or do a Fourier transformation to go from the time evolution of the molecule to its frequency spectrum. And what we found was that the frequency spectrum that was experimentally found was in very good agreement with the theoretical results. So the dotted lines here are the theoretical values of the frequencies, and the dots here are the experimental values with their bars plotted here. So what Walker is going to do now is he's going to liven up this energy spectrum for you by using his very interesting musical transformations. So now, over to you, Walker.
Thank you, Devatrita. So let's just listen quickly to some of the sounds of so this frequency spectrum. So if we apply the similar sort of scaling method from the Light Soundinator 3000, we can see them, we can basically scale all these frequencies down by 10 to the minus 11 hertz to get this distribution of musical notes. So these are the closest notes on the piano. Deva, could you hit the next few animations, please? So they're spread over a wider frequency distribution than the element sounds we heard before. So these will sound not quite as pretty, but because they sort of cover the entire piano. So first, let's listen to each of these frequencies with a different sine wave. So David, could you show us that sound?
So I'm playing the sound, but can you hear it?
I'm not. Did you? I know to share sound.
Sit and share screen with sound. Just a second. Sorry about that.
Let's see. Oh, now it's coming up. Just a second. Let me. Yeah. Just I need to change the audio. Oh, there we go. Try it again, Deva. Maybe one more time.
Okay.
There we go. Okay, so not quite as, yes, we hear it now. So definitely a little spookier than the helium dance party or the hydrogen club banger. So let's listen to a little bit more musical representation of it. So on the next slide, if we sort of take this figure and turn it on its side, we can play each of these frequencies as a melody. So let's hear this now, and instead of sine waves here, I'm using the sound of a piano, which is just a little easier on the ears. So let's hear this. So what we're hearing here, aside from just sort of a spooky like piano melody, is the actual energy levels of the time evolution of this quantum system. And so on the next slide, we can see that Deva's work has shown that we can model molecular dynamics using a quantum computer, and then we can sonify the output of that quantum computer to generate, the sound of the quantum computer's results that it has generated. But because Deva's quantum computer models the molecular system with very high accuracy, we are in effect listening to the sonification of the molecular dynamics. So I previously shared with you the sounds of molecules and elements static, just not doing anything other than just kind of vibing, right? And there has also been people who have sonified the output or the happenings of a quantum computer. But this is the first time that all three of these have been tied together. So we're not only listening to a quantum computer, but because the quantum computer is modeling a molecular system with very high accuracy, we are listening to molecules as well, with the quantum computer being our instrument. And so with that, I think, yes, so we'd like to thank all the collaborators, and again, thank everyone for organizing this event and everyone for coming out. And I think we probably don't have any time for questions. Yeah, so with that, thank you all for your time, and thank you, Devatrita, for joining us over Zoom.
Thank you.
So we'll get back to physics in a while. Don't worry, we get him all the help we need, so we can get. We did physics, we did computer science, we did chemistry, we did music. The only thing left to do next is what? What do you think? Does anyone want to take a guess? Math? Okay, yes. So math is definitely coming up, but before we get to math, we have a few people from IBM. That's a corporate. Where does quantum lead into corporate, or where does quantum lead to in real life? And that's what we wanted to introduce to you. We have speakers Jim and Brian from IBM, and they have been working in quantum computing for a very long time. Jim has developed his own library to help support people write code in Java, just like you have seen with Qiskit from IBM. You also have strange effects. And I leave it to them to talk more about their work, and also it'll be followed up by music.
Thank you.
Hello, there it is. Hey, everybody. Thanks for bearing with us, and glad you're all here. We're excited to talk with you all. My name is Brian. Hold on, the microphone's still turning on.
My name is Jim.
Yeah, there it is. We're excited. We're plugging in HDMI ports. We're not sure how to switch them over. Beautiful. Okay. First, I wanted to say thank you to the entire IU staff. I know a lot of folks did a lot of work to get all this together. We want to say a big thank you for all of that. My fiance and I were both excited to be here. Jim's not my fiance, sorry. But we are excited to be in Indiana for the first time ever. We're actually staying at Hotel Quantization, 5th floor, of course. I was on the phone with my brother. I told him I'm coming home with a light soundinator for my nephew. He's super excited. So yeah, we're really looking forward to it. But no, we are here to talk to you at first at a very basic level for those of you that do not really know what quantum computing is. So show of hands, people in this room, do you have experience with quantum computing or no? Raise your hand if you have experience with quantum computing. Okay, roughly half, great. So we are going to start our talk today. Let's see, we're looking at the right thing there, perfect. We're gonna start our talk by just doing a very quick intro to what quantum computing really is. As I talk through all that, there's these lovely books over here as well, which, let me just go 1 or 2 slides in here, and you might see a little bit about the book. This book written by this man right here, as well as our coworker, Frank. Frank Harkins, thank you. And this book is a really awesome pocket guide to using QuTE, which is the software SDK that we use to write all of our quantum code. For those of you that are interactive audience members that have a great question or that have something really intriguing you want to say, or maybe you're just super confused and you want to just raise your hand and be bold and say something, Jim has graciously brought a bunch of those books to give out to audience members who are very engaged. So look forward to that. All right, how's that mic?
Sounds good.
Beautiful, okay. So, quick introduction of ourselves. I think it's, yeah, there's our names. Quick introductions of ourselves. Jim, would you like to start a little bit about yourself?
Yeah. James Weaver, longtime classical developer, like Java and other technologies. About 6 years ago, I heard somebody mention on stage, Vince Cerf, the guy that invented TCP/IP, he mentioned on stage something about Shor's algorithm. So I did a Wikipedia search on it and was introduced to quantum mechanics. So just the idea that you could compute on top of quantum mechanics rather than just bits and bytes, you could have the richness of qubits, right, of quantum bits. And so I kind of fell into that rabbit hole and haven't really come out since.
Yeah.
So it's been an exciting journey. But now I'm a quantum developer advocate at IBM.
He's the best. So I'm Brian, as I mentioned before. I started as a middle school science teacher, hence the energy. And I joined IBM as a education-focused advocate, working with students as well as professors to help them achieve their goals of doing cool things with quantum. Hence also us being here today. So the main part of what we're going to talk about is this stuff up here, the quantum music playground. We're going to go through what that is, how it works, and how we've created music using the quantum music playground. But we thought it would be important for you to have a good understanding of what some of these foundational principles of quantum computing are before showing that. So, quick question. How many ways can you arrange 10 different people at a dinner party? I see some calculators coming out. Oh, I got a hand?
2 to the 10.
2 to the 10. It's a very good guess. You're not quite there, but you're onto something. Yes, 10 factorial, which would be 10 times 9 times 8 times 7 times 6, all the way down. That is the correct answer, which adds up to over 3.6 million possible ways. Should we give a book for that answer?
Sure, yeah.
Yeah, let's give a book. Thank you very much. Great answer, great answer. So 10 factorial ways for just 10 people. I mean, there's more than 10 people in this room, much more. But just 10 people to sit around one table, there's over 3.6 million possible ways for them to arrange themselves. That tells us that some problems are bigger than you might originally think. And so you're probably thinking to yourself, but quantum is about small things. That's what we've heard so far, atoms and molecules and all that stuff. Well, that's true. We'll move to another very classic example, which is a caffeine molecule. Many of you might be familiar with caffeine molecules or have already had many of them today. I know I have. But caffeine molecules are really small, right? It's a single molecule. And really small things behave differently than what we would expect up here in the big world. The forces from the electrons, the different bonds, the rotations, everything that you heard, honestly, in all the previous presentations today, they are all those quantum mechanical forces that really affect these small things. The way that I picture this is almost like a mini solar system inside of one molecule. All the different forces that are pulling, pushing, or whatever, that's a lot to keep track of on a classical computer. And in fact, if we were using a classical computer like this one in front of me, it would be impossible to perfectly, emphasis on the word perfect there, model all of the atoms within a single caffeine molecule. There's just too many interactions at the quantum scale for us to perfectly look at what's happening within that molecule. And so that tells me that some problems are too small for us to see clearly. But even though we don't have a computer that can perfectly model caffeine, caffeine still exists, right? Like, we are drinking it, we're using it all the time. We trust that it's something that is a substance we can put in our body without worrying that we're going to explode, right? Nature has already found a way to understand the correct way to arrange those atoms without needing to ask a computer how that should happen. So you put all that together, the big, the small, that's exactly where quantum computing comes in. It's that duality of big and small where we see value in the industry of quantum computing. Classical computers, they follow the classical laws of physics, but quantum, they follow, as you've heard, the laws of quantum mechanics, which are the laws of nature or how things behave on that really small scale. And so our scientists, like Jim and many others, have harnessed this in many different ways to our advantage. Some more artistic ways to harness that, some more scientific ways to harness that, but they're all about harnessing the power of nature, harnessing that quantum mechanical approach to create something new and unique. How's that sound so far?
Sounds great, man.
Great, okay. Any questions? Anyone want a book? You need a good question if you get a book. No one wants a book? Yeah, that's right, we'll get there. So before we jump into the music, let's very briefly talk about the qubits. You heard earlier from Walker about qubits. We're going to talk just briefly about them as well. That's a quantum bit of data, a qubit. They have these special properties, which these special properties are what we are going to use to create music. You've heard some other ways to create music. There's honestly infinity ways that you could use quantum mechanics to create music. This is just one possible approach. But those special properties that we want to focus on are superposition, number one. I'm going to just talk briefly on this. If you think of a classical bit, as you did earlier, as a single note, thank you for allowing me to use your prop. You could think of a qubit as a way to play a chord or multiple notes all at the same time. Pretend that piano just played a chord and you've got the idea. Beautiful, look at that. Didn't plan that either, thank you both. Qubits can contain a combination of different possible states or notes. But here's the rub with all of this, when you actually listen to a qubit, when you actually observe what's going on in that chord, you only get to hear one of those possible notes. Of course, nature didn't want to make it too easy for us to figure out what was going on. So that's the first thing, superposition. Remember that word, superposition. The second thing is entanglement. This is a much harder one to try and explain because we don't really have a real-world counterpart to what entanglement does. But essentially, you could take two different qubits and you can entangle them, which shares something between them. And then later on, by only looking at one of those qubits, you can learn something about the other. So there's this connection between them. That's an extremely simple way of explaining what that is. So now to summarize everything that I just went over, quantum computers use special bits of data called qubits. They follow the laws of quantum mechanics. We use that to our advantage with superposition and entanglement, and we use that to harness the power of nature. All right, so last thing here, I'm just gonna show you what a circuit might look like. Up here, let's see, is my mouse working? No, of course not. What you're seeing up here is the IBM Quantum Composer, which is a way to drag these colorful squares, which are essentially small forms of instructions. We call them gates. Wait, sorry. And then those gates send instructions to the qubits. We are going to be using those gates as we create music as well. We're going to be using those gates to create circuits, which again is just like a package of instructions. And that package of instructions is all composed up there. And that's where I finally say, let's get to the music of all of this. But just remember that it is all based on these foundational principles of superposition, entanglement, and a few others. All right, Jim, over to you.
Yeah, sorry about that. I thought I was looking at this.
I know it was one slide ahead, it's
I was
tricky.
going to interact with it. And look, we have what should we name this? What should we name that?
For a book, anyone?
Yeah, come up with a name. Okay, it's going to use quantum music to play a xylophone. What should we call that xylophone? Yes.
The Quantum Musicinator 4000.
Okay, there you go. Come on up here.
Yeah, I got it. Beautiful, thank you.
Great. All right, so Brian talked about different aspects of quantum computing. What we're looking at here is a quantum circuit. Here we have 4 wires, 4 qubits on our quantum circuit. And on this we have 4 Hadamard gates. A Hadamard gate simply puts a qubit into an equal superposition, and then we have some phase gates here. And so if, for example, if we took, like deleted that phase gate here, we would see different things going on here, because what we're doing is when the qubit is in a superposition, we are rotating it, and so its phase is changing. And so I'll reintroduce those. I'll put a T gate here, which is one rotation, and here's another kind of rotation, or another rotation value here. And as we see that, we notice a couple of things. One is there's just 4 qubits, but there are 16 pads on our xylophone. And the reason for that is for every qubit that you have 2 to that number of qubits basis states. So these down here are basis states. It's a little small to see, but the basis states are labeled in binary from 0, 0, 0, 0 all the way to 1, 1, 1, 1. So it's a binary progression. And each of those then are a different color, which symbolizes different phases. So by controlling 4 qubits, we can actually produce 16 basis states with different phases, with different values of rotation, and rendered as different colors. Also, if the colors represent the phases, the height of the bar represents the amplitude. And as many of you know, if you take the amplitude and square it, actually the absolute value of the amplitude and square it, then you are going to get its probability of being measured if you would measure this quantum state. So in this particular case, there's an equal probability of being measured. So, just like Roy, Roy G. Biv talked about, let's kind of listen to that. So, what we can do then is go to the Quantum Music Playground, and if you wanted to actually go and download the Quantum Music Playground, and I'll tell you what it is in a second. You just go to our convenience URL, qisk.it/QMP for Quantum Music Playground. And that's my repo, my GitHub repo for the Quantum Music Playground. There's a tutorial, there's links where you can download it, and essentially what it is, we have live up here. Essentially what it is, it's a plug-in to a package called Ableton Live. Ableton Live is a digital audio workstation that that music producers and DJs, et cetera, use to be able to, to DJ clubs and to compose music, things like that. So I wrote a plugin for that called the Quantum Music Playground that you see in the lower left hand of the screen, that then has a quantum circuit in it that we can then put these quantum gates on and then produce these quantum states. But to sonify it, right, to one of the millions of ways you could take a quantum state and sonify it. To do that, what we did is we said, okay, we will take these states here. Find it again. We will take these states. So these basis states, there's 16 of them here, and we'll say each one of those is going to be a 16th note. And then we'll take the rotation, and we're going to say, based upon the rotation, that's going to be a certain pitch or a certain instrument, if it's like a drum kit. And so kind of the idea then is to be able to, the reason why I created it was to be able to give people intuition in a fun, kind of musical way of what the effect is of creating and changing quantum circuits, and then being able to see the resultant quantum state and kind of listening to it. I feel like Walter stole most of our content because he was preaching to the choir, right? We're saying, yeah, people maybe with maybe one of the principal ways of accessing things is musically. Well, this is kind of the idea here, only in the quantum sense. So anyway, it's a playground. It's free and open source. You can download Ableton Live Suite for 90 days, play with it free. It's a great way to kill an afternoon, just kind of playing with it. So we're going to kill part of this afternoon just playing with it.
So where is the sound of entanglement?
The sound of entanglement. Well, I can show you the sound of entanglement. Yes, yes. Yes, exactly. We will do that. So go back to here. And so the way this maps out, here's our quantum music in nature 4000, right? There it is. And then here it is in the Quantum Music Playground. So it's the same circuit, but these phases then map out to the pitches, right? So now, if we went into Quantum Music Playground and just kind of play with that. So I'm going to go ahead and start Ableton Live. So that's what it sounds like. But then I could kind of play with it, right? Can you hear it, by the way? Everybody hear it? Okay. And so, yeah, you're going to control it. Fine, good. So another aspect of it is there's this thing called the push. you want to look it up. It's something that DJs use to control their music when they're DJing a club. They can change volume, they can start tracks, things like that. What we did is we created the ability to change the circuit on the push. And so, for example, I'm going to go ahead and just erase all these things here. And so I'm just, hitting lights and things. And I guess, here, I'm trying to turn it up, you're turning it down. Whatever you say, whatever you want. Okay, so what you're listening to right now is an empty quantum circuit. So an empty quantum circuit, if I had, 4 wires, for example, well, here we just have, 1 wire. But it's just the 0 state, or if it's 4 wires, it's the 0, 0, 0, 0 state. So all you're going to hear is just this beat. But then, if I, for example, put an H gate here, now we hear 2 beats. Now you asked what entanglement would sound like. So let's do a bell pair here. So I'm going to put a control. So now I've got an H gate with a control X gate, right? And so what you see up there, then, the result is there's amplitude on 0, 0, there's amplitude on 1, 1, but no amplitude on the other 2, right? Because they're perfectly entangled. And so if you measure it, and you measure one of the qubits, the 0, and it's 0, then the only 2 possibilities are either 0, 0, or 1, 1. So thanks for the leading question. You should give.
I have another.
Okay. So now, let's go ahead and recreate the scale there. So now I'll rotate the top qubit there, and then we have that. Okay, so that's kind of the basics. And so now I'm going to kind of live code a song, and whoever spots this song first is going to get a book.
I was going to say, what do you think you're going to get if you get it right?
Yeah, oh yeah. Okay, so so I'm going to just go ahead and live code. First of all, I'm going to select another one of these clips, not this scale clip, but this left-hand clip, which is the grand piano there. So I'm going to go into the QMP, the Quantum Music Playground, and I'm going to select the left hand. And there's no circuit there. As a matter of fact, I'm going to go ahead and make this so that it's kind of the way that it starts from scratch here. And then just kind of build it all from scratch. So when you create a new clip in Ableton, and then you hit load clips here, then it will load all the clips in. Here we've got the left hand. And some of the things we can do then is we can say, well, I want to transpose. I don't want this to be a C scale. I want to be a, maybe a couple of half steps up or whatever. As a matter of fact, I could do major scale, minor, pentatonic, Dorian, Ionian, any kind of scale I wanted to there. So just to kind of play with it, I'm gonna twist one of the buttons here for transpose and bring it up a couple half steps here. And then I'm going to do something. I'm going to change the global phase of this quantum state. So changing the global phase, what it does is it changes the whole phase of the quantum state so that everything is from that orientation. All the basis state phases are then viewed from that orientation. So I'm going to go to pitch, or to phase here. There's a little button here for phase. And then I'm going to twist this phase shift button to where I get up to this note here. and then I'll put pitch back. And so now I'll go ahead and play that. So any guesses on what it is? It's not one note sound, but what is it? Marianne, not yet. No, that's pretty good though. Can you sing? Okay. So anyway, let's go
Sounds
back.
like The Reason Is You by Hoobastank.
Hoobastank, yeah. Yes. Okay, so yeah, not much there, right? So let me put some Panama gates here. So I've got, 6 wires here. Some of them empty, but 6 wires. 2 to the 6th power. How many 16th notes do I have? 64 16th notes, right? Okay. But they're all the same. It's kind of boring. So kind of the philosophy that we've used for this is the Hilbert space, whether you put Hadamard gates on there or not, the Hilbert space seems to want to, which is, a Hilbert space is a way to model quantum states, right? It's a complex vector space. And so this Hilbert space then wants to sound pretty monotonous. You know, it sounds a little bit melodic, but just kind of monotonous. I would want this to sound like maybe some music that I'm already familiar with, maybe on the radio. But in order to kind of compose with this, what we do is kind of co-create with the Hilbert space. So we kind of tweak the quantum bits ever so slightly to where we kind of coax a melody or things that it wants to sound like with very little coercion. So we're kind of cooperating with the Hilbert space. So I'll do that. So what I'm going to do then is maybe I'll put a phase gate there on that top qubit there, the one that's the first one that's got that Hilbert space. And maybe I'll put another one here. Maybe I'll just play with this one a little bit. Just kind of playing with it, right? Just kind of seeing what sounds good.
See some light bulbs going off right now.
The Canon in D.
Hey, let's get a book over here. And then for the microphone, say what it is.
Canon in D.
Very good.
Very good.
So with very little, 3 phase gates, we're able to get at least the first few notes of canon in D. I think the Taco Bell maybe had access to the Quantuminator 4000. I think so. Maybe he got some creative influences. So, well, wait, it's not quite right yet. So what do we need to do? Well, about halfway through this quantum state, we need to change that note a little bit. Well, about halfway through, that's going to be where the higher order qubits, the last half of the ones in the state vector are the high bit is 1. So we're going to then play with we'll play with the rotation on this top one here. Not quite yet, though. Now, we're going to have to torture the qubits a little more to be able to kind of finish this one out, that melody. And to do that, Brian, I'm going to change the preferences here so we can see it all. my colleague over here said, we're gonna have to use entanglement. And so I'm gonna put a control gate here. And then I'll use some entanglement here. Okay, so we have the basic one, right? Okay. So now what I'll do, I'm pretty happy with that. That's the left hand, but now I'm gonna go to the right hand. So I'm just gonna copy this clip over to the next track. So I'll paste it there. I'm gonna rename it. Did anybody see, by the way, it was a Let It Be with the Beatles. It was the Beatles movie. It was about how in their last recording sessions they were preparing for the Let It Be kind of concert. Anybody see that?
That documentary came out like a year ago.
Documentary, yeah. No, okay.
It's very good.
Yeah. Very good. Not relevant, so somebody else saw it.
But I do have a suspicion that many of you saw the clip that we wanted to talk about. If you saw that part on maybe on YouTube of Paul McCartney just sitting there strumming along, kind of playing nothing, and then stumbling into one of the Beatles' biggest songs within like 3 minutes of just picking around. Does that ring some bells? Okay, there you go, Jim.
So this is kind of the idea, where you're letting the Hilbert space, you know, because it's like Paul was just kind of strumming his bass, so just a couple of strings on the bass. And then he started kind of, you know, singing to it, and they would change what he was strumming. And so this, through this process, almost this variational algorithm, right? This process, Let It Be came out. And so that's kind of like what we're doing here, where we're letting the Hilbert space kind of play, we're tweaking, we're seeing what it sounds like, and we're cooperating with it. And this must have been what Pachelbel did too. So now we've got the right hand here. I'm going to hit load clips, since I changed the name of that. I'm going to go to the right hand. And I'm going to go ahead and change the octave. Well, first of all, I'll go ahead and now we can hear it. So I'm going to change the octave. Okay, so now we've got the same thing, right? Because I duplicated the track. I duplicated the circuit. But now I'm going to add some things to that. So I'm going to add a couple half mark gates, right? So we've got another 2 qubits that are in equal superpositions. And so you probably know what I'm going to do now, right? I'm going to start tweaking. And I'll tweak this one here too. So now we have this kind of jazzy version of Pachelbel, because we're into you know, major 7th chords and minor 7ths and things like that. So I'm going to have to resort to a little bit of entanglement there too, to kind of pin down that high note of those chords, the 4th note of the chords. So I'm going to put a control qubit there. And then I'll bring the rotation down. Okay, so there we have then kind of the right hand of Pachelbel's canon. And so if I wanted to then hear, rather than an arpeggio, if I wanted to hear all at the same time, I could hit the quantize button here. I just kind of play with that if I wanted to. I'm going to take the quantize button off though. So now we'll go over to the flute track. And, now we're at the flute track here, and we're in C, so I'm going to transpose up to D. And we'll put some Hadamard gates here. And I'm going to change the global phase. I'm going to change it to where we start at. A third above the major scale. start to listen to it here. And so we better start tweaking some qubits here. To now use a little more entanglement, right, to pin down the last few there, last couple things that happened there. Okay. So now maybe I'll put another hat mark here and tweak that a little bit. And so just kind of playing with it. Now we end up with what Pachelbel's can. But that's all deterministic because we got to peek inside the quantum state and use it before measuring. But maybe we want to measure to kind of compose music by measuring. And so what we can use is this stochastic button. And if we don't like that one, then we could hit stochastic again. And it will then do measurements as well. And what's happening is for every beat that has any amplitude, it samples the entire distribution of the quantum state, and then for each one of those things, then inserts a note. So anyway, that's a little bit about how we can co-create with the Hilbert space, kind of doing a give and take between what it wants to sound like and what we would choose to have it sound like. So any questions on that? Yes.
So like, what is the phase of T, and like, what does it do to like one note?
Okay, so what is the phase of T?
So like 90 or 180, I don't remember.
Right, so what is the phase of a T gate? And what does it do? So each of these letter gates have a different value, right?
Yeah.
So a Z gate, a Z gate, has what's called a pi rotation, which is 180 degrees. An S gate is half of that. It's a 90 degree. A T gate is a 45 degree, or a pi over 8, or pi over 4 rotation. Okay. Other questions? Yes.
What was the stochastic method you were talking about? So you're saying that every time you hit the button, it's going to be a different, settlement of or measurement of
Exactly.
So
Exactly. So
could you
that's a
explain
good
that
question.
more?
So the stochastic button, what it does is for every 16th note here that has any amplitude, it's going to, instead of playing what we asked it to play, right, because of our quantum states, and what it's going to do is, instead of playing that, it's going to take any of those basis states with any amplitude at all, and it's going to then take a measurement on the entire quantum state. And whatever that result is going to be, what the one of those basis states, or actually one of, yeah. And so what it's going to do is then play the phase that corresponded to the basis state that that it measured. So, so here, the only possibilities that it would have would be one of these notes. And so it's doing a measurement, and if the result of that measurement was this basis state, for example, then it would use that phase to put into that particular note.
So it's indeterministic?
Right, it's,
And then
right, it's not
all happening at the
deterministic,
same
it's
time?
quantum measurement kind of thing, right?
Are all the notes essentially like measured at the same time? Like,
Yes.
They're not measured at from different, just sampling, like different populations.
Right, it's measuring one, for every one that has amplitude, it's measuring that many times from the same quantum state, the same distribution. Thanks. Yeah, thanks for that question. Another person that hasn't had a question, yes.
Yeah, so I'm curious if each of the pitches and rhythms that are being output are represented by the orientation and form and binary output, is that right? The binary numbers. I'm curious if they always have a certain pattern or formulaic nature to them.
Mm-hmm.
Like, is it possible to take a piece of pre-existing music and actually like represent it?
Oh,
into
my goodness.
Oh my gosh. Did you see our slides?
Yeah, who is this guy? Here you go, Plant. It's a
Yeah,
perfect
so-
segue.
So now Brian's going to get into that, and then whoever needs to throw us off stage, please do, because I want to be respectful of the next presenters. So let us know when we need to get off stage, or we need to jam. Okay?
That's a great question. That's going to lead us into kind of the next part of this, which is, can we use this to kind of recreate other music, maybe not so rigid of music? First, I want to just jump into the existing track here and show you how quick you can add some percussion on top of it. My goal, 2 minutes or less. Here we go. So we're going to start with the snare drum. Oh, okay. I got it. I'm good. Thank you, though. I'm going to start with the snare drum.
Was I standing close to you or something?
No, I kind of like the challenge.
Making you uncomfortable?
I like the challenge.
Okay.
All right, snare drum goes on 1 and 3 or 2 and 4?
2 and 4.
2 and 4, thank you. Oh my goodness, you would not believe how many people get that wrong. So, we're gonna drop a snare. Good, I'm a drummer too. We're gonna drop a snare, we're gonna unmute that. All right, let's get some hi-hats in here too. I'm gonna jump over to my hi-hats. Let's unmute those. I went the wrong way with that, didn't I? Let's try this one. There we go. All right, so I want this over here. Beautiful. I think I'm at minute 30. Let's go over to my bass drum. Unmute that. Great, now we've got some drums. Very quickly with the Quantum Music Playground, you can add in a lot of extra pieces. You can hear how things are going to sound. You can mess around, which is exactly what we wanted to do when we started to recreate existing music. Because we wanted to say, can we take the Quantum Music Playground and really recreate some EDM music? Some deep house, some really type of stuff. And we started looking at what that music has, what types of patterns you might see in EDM songs, in kind of house music. I'm going to refer to my notes here, so I apologize for looking at my phone. But we noticed that there was some really strong, helpful patterns that do show up in EDM music. And I'm going to turn one of those on right now as I continue to talk to you. We'll go with Purple Line. We'll mess around with it. This is a good example of messing around with the Quantum Music Playground and then hearing something fun and then saying, oh, let's figure out how to make that fun. So the Quantum Music Playground is something that you can use to make music. I'm stepping over here to make a dramatic effect. But as you heard earlier, right, there's an infinite number of ways that you really could figure out your own version of music using something quantum. We are focusing on that Hilbert space, which is what Jim mentioned before. That's one of the most common ways of modeling a quantum state. And we're kind of pushing and pulling against that Hilbert space to find what we want. Now, if you don't know what that term means, if you didn't follow the math behind it before, that's okay. You really don't need to. You just have to know that it has something that it's trying to do instinctually. The Hilbert space has kind of a very basic version of what it's trying to do. By the way, everything you're hearing right now, we created using the Quantum Music Playground. So left to its own devices, the Hilbert space wouldn't be much help to us. But using that superposition gate, that H gate that I mentioned earlier today, that's how we can take one note and turn it into 16th notes. Using the X gates or the control gates that Jim was showing us before, that's how we create syncopation, or beats showing up on more than just downbeats. And then using the phase gates, that's how we shift between instruments or shift between pitches on the same instrument. So EDM music, those patterns I was talking about before, well, one of the really helpful things is that it has repeatable phrases. So you can see as I'm talking, Jim is going through some of the different clips that we created to play what you're hearing. They repeat, right? They repeat over and over. Sometimes my bass drum is repeating pretty much this entire song, but then other times, like this clip you're hearing right now, we only use one time throughout it. But we create that clip, and then using an arrangement view, we drop them in where they need to go. The cycles that tend to come out of EDM music are also very easy for us to use with the Quantum Music Playground. Kind of that A, B, A, C structure, especially dropping into these big choruses or some type of preamble. There's a really fun way to make a beat drop on the Quantum Music Playground that maybe some other day we'll show you. But just to finish with all of that, the act of creating music is inherently quantum. We are using these technologies to our advantage. We're using that process to our advantage, like Jim was mentioning before with Paul McCartney, doodling around, finding the good, amplifying that, and finding the negative and dropping it off. And that's where I'm gonna leave you. Thank you very much.
Do we have time for any more questions, or should we just go
We
ahead?
have like 7-8 more minutes for questions. Or
Okay, so question? Yes.
It's a bit different from this, but I wanted to know if you can sort of take animal noises, probably dolphin syllables or cat syllables, and map them into this.
Why not? Why not? Why? Instead of being like different instruments, like in a drum kit, snares, clap, things like that. Why not different dolphin phonemes, right? Yeah.
And then map them speeches with this and what it makes.
Yes, that would be awesome. You should do that. You should download that. It's free. And you should map some in there and then do our next presentation with us. Other questions? Yes.
So, do you think that superconducting beat or ion beat or qubits, they will sound similar or different?
Do I think what?
I mean, the qubits with superconducting or ion.
Okay, so
are they
would they sound similar? Right. Okay, would they sound similar? So at this level of abstraction, right, we are working above the level of the physical. We're working at this abstract qubit kind of thing. So you'd have to talk to the person behind you to get an answer to that question. But at this level of abstraction, they sound identical because we're dealing with.
Is there any way if I can play with that, I can make a difference, hear a difference?
Yeah, you could. Yeah, you can come up and play with it afterwards. Yeah, it'll be fun. Yes.
Have you thought about reversing the process instead of like using quantum, like making quantum like networks or circuits? Instead, making music turn into quantum circuits.
Yeah, so like synthesizing a circuit.
Yeah, so that you program basically circuits with music itself.
Yeah, that would be cool. Right, so.
Like estimate the ability, like we can basically put like some song and then see if it has actually functional use.
Yeah, so my colleague over here is proposing a paper that I'd be happy to contribute to if you'd like.
Okay.
Yeah. That will be on archive, I think, next year, where he takes a simple melody or maybe a complex melody or beat patterns or whatever, and brings it in and synthesizes it into quantum circuits, and then they play here. And yeah, sounds like a great project. Please do that. Did you get a book yet? Okay. Any other questions? You've been a really great audience, by the way. Yes.
So far we've mainly covered like implications of quantum computing in terms of music and audio data. But what are some effects in terms of data analysis and trying to actually analyze data in terms of like audio files and potentially moving on from like an MP3 or MP4 data frame and going into like a smaller, more compact data set?
Okay, that's an interesting area of research, you know, where, and it's kind of a one-off from this, but the idea of being able to take raw audio files, right, waves, things like that, and then extract quantum information and then represent them, kind of like we did in the old days, right, where we take raw audio and represent them with bits, represent them with qubits. And so one of our colleagues, Eduardo Miranda, who's just a pioneer in this space in the UK, the University of Oxford, I believe, is actively exploring that kind of thing. Yeah. So thank you very much, everyone, for all your great questions.
Thank you. Thank you.
I think we're going to get to play a little bit here.
Hello. Hello, everybody. My name is Alex Solani. I am currently a junior undergraduate in the Jacobs School of Music studying oboe, and I'm also vice president of Quantum Technologies for Everyone. And first of all, could we just give a hand for all the speakers we've had so far? So we're going to play a little bit. So Jim Weaver will be on guitar, Brian Ewenson will be on drums, Alex Corbetti will be on bass, Dmitry Volkov, who is also in the Quantum Technologies Club, will be on trombone, and I will be on trumpet. So we'll be playing an A blues for you, just 5 courses. Woo!
Okay, so that was thoroughly entertaining and educational. I hope you guys learned a lot. And I hope this day is quite interesting to you so far. It's only going to get even more interesting for the next 2 hours. So a little bit of story. We started this club. It's called Quantum Technologies for Everyone. We started it a year back, last semester in fall of 22. And we didn't know what to do. We wanted to get the message to everyone that we're starting this club. And then when we talk about quantum, people say, I don't understand quantum. I've never done quantum. And I have no idea. I've never taken a physics course, or I've never taken quantum physics course. I don't know what to do there. And that's where the misconceptions begin. You don't really need to know quantum physics to do quantum computing. And that's the whole point of this day. You have seen so many people talk about their passions in quantum technologies and share their knowledge here. And we had a similar goal in mind. We wanted to educate everyone. So one of the ways I wanted to do that was by winning competitions. We are relatively new, and if you know that for the first 2 years of any club, if you don't take off, it's always going to die out. You can see a lot of ghost clubs in Indiana University right now. Okay. We want people to join, we want people to be interested. So starting from 5 people, we have 30 to we have 100 people now in this room, and we want to keep going. I wanted to add a little bit more. So we wanted to see who else is doing the same thing, who else is also talking about quantum all across the United States, all across the Americas in general. Okay. So one of the ways was by going and attending competitions, hackathon, workshops, and winning them. So you'll be surprised to know, we have Micah here, right? Micah has never taken a physics course in his life. In fact, he's a business student. He's a Kelly student.
Hey!
Yeah. Okay. He went, so I told him, we have this hackathon happening in MIT, and we want students there. We want students there representing Indiana University. He had exams. He said, I have exams, I cannot go. I said, okay, so you finish your exams and then go. So the competition was in the end of January, somewhere around January 23rd to 31st. And he drove non-stop for 16 hours all the way from here to MIT. He won the 3rd place in the Quantinium Challenge. And then he drove back 16 hours to attend his classes and give his best in the exams. I don't know how you did in the exams, though.
It's okay.
So that's the idea here. We want everyone to be interested in this field. It's going to be a thing that you're going to keep hearing in the next 5 years, like you have ChatGPT right now. I'm pretty sure you open your news feed, every 4th or every 3rd feed is about ChatGPT. That's what's going to happen with quantum in the next 4 years. You want to be ahead of that curve. And so a shameless plug. If you're interested, please join the club. And another interesting, what happened?
Yeah, they have to scan it.
Oh yeah, sorry, my bad. So, another interesting thing that happens in competitions is you get to meet people who are like-minded, who have the same passions in quantum technologies. And we met a lot of people who had appeared at MIT. We met someone from UT Austin, University of Texas at Austin, and they were similarly interested in attending Quantum Day, but they cannot do that. So we gave them the option to speak online, and that's who's coming up next. So I hope people are still online. Aishi, if you can hear us.
I can you?
Yes, you're good. So you can start sharing your screen, and we can hear you and see you, and you can talk about your interests.
Okay, I don't know how to share screen. There we go. Yeah, so, yeah. So first of all, thank you so much for inviting us. I'm representing the Quantum Collective, my name is Aishi Guha. And I'm an undergraduate researcher, so I'm a third year, so junior physics major at UT. Yeah, so thank you so much for inviting us to this exciting event. And I'll be talking about my project, entanglement swapping, which is what I've been doing at UT for a little bit. Yeah, so I don't know if it will go. There we go. So a little bit about the Quantum Collective itself. It has similar goals as the IU club. So we are interested in making quantum accessible for all UT students. So sorry. And we have 4 core pillars: learning, getting connected, doing research, and discovering opportunities. So we have research groups, learning labs, reading groups, and hackathons. One exciting thing coming up is the SQUID conference, which is where our participants will be presenting like survey papers or actual original research in a conference setting at UT, and also with the coalition. So yeah, that's just a few pictures of us. Hopefully it will work. So my project itself is, it involves classically simulating entanglement swapping, which I'll go into a little bit. Yeah, and I did this work with Dr. Brian LaCour and Dr. Noah Davis. So what is entanglement? I think it was covered in the last presentation a little bit, but I'll just go into it a bit. So what you do is you can get a pump laser. You can pump it through a nonlinear crystal. In this case, it's beta barium borate. And so that can do a process called spontaneous parametric down conversion, and you can get 2 photons that are entangled. So one way to entangled is if one thing is like a spin up state, the other will be a spin down, or vice versa. Kind of a nice way to think about this is that, if that one is a left shoe, you know for a fact that the other one is going to be a right shoe. That's just how it's entangled, so it's not separable. So entanglement swapping itself, that's just another picture of 2 entangled photons going through a crystal. Entanglement swapping itself is when you take 2 photons that have never interacted before, and you entangle them through a Bell state measurement. Bell state measurement is basically kind of a way to tell what Bell state something is in. And there's 4 of them. We're focused on the psi minus state, which is if one thing is a horizontal photon, the other one would be a vertical, or if one is a vertical, the other would be a horizontal. It's kind of like this. You can also say horizontal is like a spin down, vertical is a spin up. So yeah, those would be opposing. So this picture here, I don't know if you can see my cursor. My screen is sharing, right?
Yeah.
Yeah, so I don't know if you can see my cursor. So the EPR source is basically the entangled photon source. There are 2 of them. And so 1, 2, 3, and 4 are 4 photons. 1 and 2 are entangled initially, and then 3 and 4 are entangled. 1 and 4, notice they are not entangled with each other. 2 and 3, what we do with these 2 is we do the Bell state measurement, and that heralds whether or not 1 and 4 will be entangled. And so that's basically how that system works. Now, why are we interested in entanglement swapping? Well, because you can take this system and you can kind of chain it along, and you can create a quantum network. So that's the basics of entanglement swapping. My project involved making a physics-based classical model of entanglement swapping. So there's a picture of the scheme here. So the 2 entanglement sources are in yellow. And I mean, it's just kind of representative of 2 photons coming out each way. This isn't what an actual setup would look like. Anyways, so A1, B1, those photons go into that Bell state measurement system. So Charlie here is doing the Bell state measurement. And what we do is we put a beam splitter in there, which through it's kind of like a poor man's Bell state measurement. So if these 2 arms from here are both detected on D6 and D5, so if both of those detectors go off, you know that you have a horizontal photon here and a vertical photon here, and depending on that, we can tell if there has been an entanglement. Entanglement has happened in the other system. So what we would look for is essentially D1 going off and D4 going off, or D2 going off and D3 going off. depending on if Charlie detected a Bell state. Yeah, so that's the Bell state measurement part, and then QST is quantum state tomography. That is used to actually measure the fidelity of the system by cycling the PBS through all 16 combinations of Pauli matrices. So the model itself, we conducted sweeps of the parameters for the QST detector thresholds. So it's D1, D2, D3, D4. Detection threshold is kind of like the opposite of a dart count in the model. So, so threshold, if you can think about like a bouncer at a club, if the bouncer has really high standards, they won't let people in. They'll let less people in. So threshold is higher. If the threshold is really low, anyone can come in. Any photons can come in. So it's more photons, more dart count. So same thing is we have a BSM detector threshold, which is the D5 and D6 detectors. And R is squeezing strength, which is kind of like a measurement of the total input power, or how many photon pairs are generated. It's just how many photons there are. And fidelity is calculated using the density matrix that is produced from running this simulation. And it's just this psi minus expectation value. Yeah, so we got some results. And these are just fidelity graphs. It's kind of like showing the lay of the land for the parameter sweeps. We put, so yeah, we do a sweep of R against gamma A, keeping gamma B constant. And then this is gamma A and versus gamma B for constant R. Basically, what we find is that the highest fidelities are produced for squeezing strengths that are moderate, so around 1 for the model, that's the number. But if it's too high, it becomes like a little bit too much like a classical system, and if it's too low, there's not enough counts. And then fidelities are optimal when the QST detecting thresholds, so the ones used for the fidelity, when they are quite a bit less than the BSM detector thresholds. For the model, we achieved a fidelity of 0.96, plus or minus like 0.009 for these parameter values. And one thing I found interesting was to run it for keeping both gamma A and gamma B equal to each other. This is more similar to what actual experiments do, is they keep, there's no way to, there's not like a direct translation between changing the threshold on this model and changing the threshold in a real detector. So they just kind of keep the same detector, hopefully, for the whole system. And what we find is that the fidelity is actually very close to what actual experimental results are like. So we get a fidelity of 0.81, plus or minus 0.01. And so I think that is kind of supporting the fact that this model is a good model for real experimental processes. Anyway, so comments on efficiency. So obviously this is a classical model, so it's a local hidden variable theory, which means that we're using a detection loophole, and our efficiencies are pretty low, which makes sense, but that's still, it's still producing these results that are on par with actual experiment. So yeah, so this is basically a graph of the BSM efficiency, which makes sense in that if you reduce R all the way, you will get absolutely no counts, and if you increase it all the way, you get 100% counts. And QSC efficiency is kind of capped at like 20%, but it's for the lowest efficiencies we get the highest fidelities, which makes sense. So in conclusion, it's like a classical spoof for a quantum system of entanglement swapping. If we can reproduce the Bell inequality measurement and the fidelity measurement, it is necessary to also measure the efficiency so that you can kind of distinguish between this classical spoof and a quantum system. And another interesting thing was the model produced so we did, on the right here, you'll see the original state is basically just measuring the original entanglement. That's just one SPDC, and if it's shooting out 2 photons, you're just measuring that. and then a swap state, and we did the fidelity of both, and we found that for certain gamma A values, the swap state actually had a higher fidelity than the original entanglement, which is kind of pointing to some sort of entanglement distillation, depending on changing this parameter. So you can kind of get like a purer state just through swapping the state through a specific parameter regime. So, all of this kind of points to a possible path for experimental exploration, specifically having like different BSM and QST detector thresholds. That might help you optimize fidelities higher than previously seen. Now, how exactly to translate between the detection threshold in this model and actual experiment, that's something to figure out and work out. So yeah, that's my presentation, and thank you so much for inviting UT to speak at this event.
Okay, thank you, Aishi. We thoroughly enjoyed that. That was interesting. So we had people from UT Austin. We had people from all over the world. We had people talking about their interests in quantum. What's next? Anyone want to take a guess?
Linguistics.
Sure, linguistics. I don't know if the next speaker knows as much linguistics though. We're missing something. We didn't represent Hoosiers yet. Where are the Hoosiers? What's happening in our background? Yeah? So to talk about what's happening in the physics lab, in Rishem lab, in IU, I'm going to introduce you to Wes, Thomas Wesley. He's a PhD student in Rishem's lab, and he's going to talk to you about his interest in what Rishem lab is up to. So,
let's see. So I have a very quick presentation to give to everybody. My goal for my talk today was to more or less make people aware of what is going on here at IU and some of the resources that have, newly been created for students to pursue quantum technology or quantum computation, I guess, in general. I'm actually a master's student at the moment doing in IU's newly made quantum information science program. But I am, and I'll talk more later about it, but I am planning to stay in the form of a PhD as there's a lot to learn, and my interests in the topic have exponentially increased over this year. So to get started, I guess I wanted to just highlight the things that I found interesting when I arrived, to begin the program, and I guess what things were interesting to me. These were a lot of the things that I think I naturally fell into as I started the program. And so the top two lines up there, that you can't really see, sorry. Those two are what I consider to be the bulk of my research interests and what I've most actively participated in over the past year. Just keep going here. Sorry. So to break it down into two, I guess, high-level projects, and I don't want to, get into too much of the details because this is, ongoing work, but I think it's exciting to share, and I think it's exciting to share for anyone that is interested in the club. And I'm just curious, how many of you are IU students? And how many of you are undergrad or graduate? Or undergrad first? A lot of undergrad. Okay, that's good. That's interesting. Just curious. How many of you are high school students? Okay, nice. All right. So when I think of quantum information at IU, I immediately think of Professor Phil Risherm and a lot of the work that he's doing in his ion trapping quantum simulation lab. So I know this was talked about briefly before. I think one of the new technological breakthroughs for developing qubits is this ability to trap individual atoms, and that is exactly what we do in his lab, and it's the utilization of the atomic spin states of these atoms that give us the ability to perform a particular computation or method of simulation to maybe learn something. So I guess long story short, with this project, all I really want to say is what I think is important is to think about the problem that you are trying to solve. And in attempting to address that problem, you will often find other applications for the work that you've been developing, and that's kind of what's been happening with this theory project that I've been working on. Again, I don't want to get ahead of myself because this is all still ongoing, but the goal of this project was to take a Hamiltonian, which is just a operator that consists of the total energy of some specific atomic molecular system. The goal was to take a Hamiltonian of that form and see what could be, what kind of Hamiltonians of this structure can be simulated with maybe our ions or a different ion trap that exists in the world that has some technical capabilities that we might not be able to reach. And so with this has kind of evolved into a bigger project that doesn't only contribute to quantum chemistry and the simulation of chemical dynamics. It's kind of grown into something that could be more generalized to anything, to any sort of finite difference solver or algorithm. And so I think I'll leave it at that. For that, this is the other. If I was to umbrella my work into two sections, I think this is the other thing that has taken a lot of thought and will continue to be a large part of my future here at IU. Not only that, I think it's exciting. A couple weeks ago, I think our club had a talk from someone, and I can't remember his name, unfortunately, but from QuTE and what they need for quantum networking and making that actually, applicable and something very useful. And one of those things was this need for a quantum repeater processor of some kind. And when I heard this, I was just thinking in my head, this is very brand new, and I didn't know if I wanted to discuss this until I saw that there was some public information over this at the FAMES Lab website, which maybe I should explain more what that is. The FAMES Lab here at IU, it is up at MESH, the Multidisciplinary Engineering and Sciences Hall. It is ran by Professor Gumenik, who works in the Luddy School of Engineering, and it is the acronym, it's very hard for me. He manufactures fiber optic cables. And I can't remember the acronym to save my life, and I apologize. But there is there's this idea that I guess was proposed to integrate a linear chain of ions in this fiber optics cable, and this would, in a sense, give us the ability to upscale quantum networks in general, I guess. And I think that's as much detail as I'll go in for that. And so I guess I want to talk a little bit more about just my experience. Throughout this program, I was wondering, I find it to be a very research-motivated and self-driven program. It's very new, there's a lot of flexibility, and there's a lot of ways to accommodate your research interests. And so I personally am an experimentalist at heart. I think I found my strengths throughout my undergrad to be in experimental physics rather than theory. And I want to also just thank, in general, all the members of Professor Phil Rasherm's lab and everyone in the physics department and everyone involved in the new QSEC, the Quantum Science and Engineering Center, because really this environment is what's shaped my outlook for like my academic future and for what I see can be done here at IU. What is next for me? Like I said earlier, I've fallen in love with ion trapping so much that I've decided to stick around for a number of more years. Not only that, I think it's without a doubt what I want to do. I think any physicist can tell you that they're more or less lifelong learners, and you know, I want to be able to pursue this kind of research at the utmost technical level as possible. And so, yeah, I guess thanks a bunch for having me. I hope everyone learned something from today. I will say, I know Professor Baxter said at the very beginning of today, I never would have thought a talk like this would happen in Jacobs. And I definitely agree, and then I was thinking to myself more and more, I was like, is it really that unexpected though? Because Walker, your presentation with quantum music was very impressive, and I think that's very clever, and that's not ever something I've thought of, you know, and so, yeah, I just want to thank everybody. I like how much this club, it tries to include everybody from all backgrounds and goes above and beyond to try to bring everyone together. I'm definitely one of the guinea pigs in this new master's program. And so I'm happy to, answer any questions or share any advice I might have for anyone interested to, do something similar, do it here at IU, or I guess is just interested in the topic in general. So, thank you.
So thank you, Walker. That was what we're doing in Phil Rasherm's lab, and I'm pretty sure you're excited about what's next, but I want to share with you a couple of stories and a couple of things that I think that you all should learn before you leave here. So the first thing is, this thing on?
Yeah,
good. Okay, the first thing is this. Why is there no break in this conference? Okay, so it's a person's history. Move this down. Okay. So the history is about government of India. So I'm from India, by the way. So back in 1970s, the government of India wanted to push education as much as possible. Okay, the way they do that is they get the students in. The classes go all the way from early morning at 9 o'clock to like 3 o'clock. Similar times to what happens in the United States. But then you also have to give them a break, because every 4 hours you have to recharge when you're studying. I'm sure you have felt that too whenever you learn do exams or whatever. So what they saw was they couldn't really afford to pay these guys anything. Teachers are still underpaid, by the way. That's a common story everywhere. They made these students come into class, and then they would have their 4-hour sessions. The lunch breaks at around 12 to 1 o'clock, and those guys would just go home. And since that was lunchtime, they couldn't get food anywhere nearby. It was 1970s in India. You didn't have a lot of options to go and eat out. You didn't have Panera bread, I guess. Okay? So these guys would just go home, have a heavy lunch, and then go to sleep. Okay? That's something that Indian government countered by offering the midday meal. There was a scheme there. So they had the midday meal scheme, and that's how they combated that. But that's my history of why there's no breaks here. We had a similar history with one of the conferences we attended in Chattanooga, and people would just go on breaks and never come back. Okay. So The point of the story is, if you want a break, if you want to stretch your legs, you want to drink water, please feel free to do so. There's no pressure. And that's the one story. There's a second story that I want to tell you before I introduce the next speaker. The next speaker is from Argonne. I'm going to introduce you to her. But before I do that, you have been here for around 3 hours now. I'm going to take a reference that you have had no exposure to quantum. If you had, it's perfect. If not, fine, fair enough. So the reason is, in 2020, during the heat of the pandemic, there was a rise in number of scam calls that are going on. If you're aware of scam calls, the scam calls will just call you and pretend to be FBI, Department of Justice or whatever, and then ask you questions like, can you download this app and use that? And my father almost fell prey to that because he didn't know anything about technology. And this is going to happen when you start working with AI, you start working with ChatGPT. And if you go home and show this particular video to your friends, I'm pretty sure none of them can understand what's going on here. But since you have been here for 3 hours, I hope you can make the difference, make out the difference between what is real and what isn't. And if you have seen this before, this is how I start off my classes and end my classes in quantum computing.
Oh my gosh, this one?
Yeah. Have you seen this? There's quantum shoe, there's quantum consciousness, there's all sorts of things. Not, oh, it's not Canadian Shark Tank, I guess. US.
The kids
the dragon.
Not able to find. So quick, yeah, this one.
Once you meet with a TurboTax expert,
don't do TurboTax. This is not my computer. Okay, ready?
Hello, Dragons. We come here today offering 20% of our company for $100,000 investment.
Hi, Dragons. I'm a chiropractor. The devices I have developed are with a team of physicists, and they change the atomic structure of the components of these devices to cause the nervous system to respond when you're wearing them. And as a result, the muscles work better and the joints work better as well. So the technology, as I say, was developed by physicists, and it creates a phenomenon called quantum entanglement. That means that there's a flow of energy between the three cliffs, and at the same time that energy pattern intersects with the central nervous system.
For 30% for $100,000, you get the resources of all 5 of us.
That sounds good to me. What it does is create a phenomenon called quantum entanglement.
okay?
They treat the contents of these devices in such a way that it draws an energy into it and disperses it in a linear fashion.
I actually know a lot about quantum entanglement. What are the other real-world applications?
Well, healthcare for sure, and the elderly for sure.
Okay.
My mother, she says, I just feel like I'm going to fall over, but when I put the device on, I never feel like I'm going to fall over because it helps regulate her balance.
That's crazy. Seems too good to be true.
It is.
So, the moral of this story is be aware of what's going on around you, and if you don't understand something, it's perfectly fine, but try to understand what's going on. And the second moral is, if you ever go onto Shark Tank, remember all the buzzwords we talked about here? All applies. These guys walked off with 500,000, by the way. So if you ever got scammed before, you're not alone. People in Shark Tank also get scammed. Okay, so let me introduce you to the next speaker. The next speaker is from Argonne National Labs. She is Tanvi Malik, and she's going to talk about AI and machine learning. So there's quantum computing. That's basically a computer, and what we are talking about is application software. We have applications in music, and as AI and machine learning is something that's really interesting and trendy right now. There is quantum machine learning as well. So I want to give you some background or give you some information on that, and I want you to leave here with all the various technologies, all the various fields that quantum computing has been applied to. So without any further ado, I'd like to hand over to Tanvi Malik.
Hello everyone. Today I'm going to talk about machine learning on spatial temporal data. So I'm a assistant computer scientist in mathematics and computer science division at Argonne National Laboratory. So before going to my talk, I just want to introduce myself. So I did my PhD, master's and bachelor's from India, and then prior to this position, I was a postdoc and MCS division at Argonne, and before that I worked as a senior data scientist at GE. My research interest is scientific machine learning and high performance computing, and earlier I worked in computer vision and image processing during my PhD. So today I'm going to talk about first few applications where you regularly see, for example, traffic. So traffic is a major problem for nowadays. Like you get congested, like people get congested in highways, and that is a loss for the economic as well. So accurate forecasting, minimizing congestion, mitigating those things is a very important issue nowadays. And traffic is spatial temporal in nature because the traffic at one particular location get impacted by all the nearby locations. So it's not just the time series at that point of at that location, but is getting impacted by all nearby locations. So this data is spatial temporal in nature, and if we can forecast traffic accurately, then it can be beneficial in mitigating congestion and real-time decision making and all other things. The next one is predicting global climate. So most of the climate models are mostly based on partial differential equation, based on the first principle, and those simulation models are very expensive. So it's very important that if we can build a data-driven model based on the data and predict climate accurately, that's very important. The next one is pandemic, and all of we know the impact of pandemic. So this is also very important to forecast it accurately, model it accurately, and this data also is spatial temporal in nature because it was spreading in the nearby area very quickly, and that was so modeling those things is really impactful for real-time decision making and other things. And the last and final example is power grid. So in power grid, sometimes they generate more energy, sometimes less, and the distribution and the demand, forecasting the demand is very important to accurately distribute the power over network. So here, all this example I have given here is from public health to climate science to transportation to wide area network and all other applications. For example, power grid, quantum chemistry, all this data are spatial temporal in nature. So if we can model this spatio-temporal dynamics very accurately, that's gonna help us in many scenario in real-time decision making for the stakeholders, and it will be helpful for economy also. So with that, I'm going to introduce about one of this application on traffic, and I'm going to talk about a little bit how we do this traffic modeling using machine learning approach. So this is highway traffic, and here our problem is that we want to forecast traffic given our past data. For example, here the input is road network and past traffic metrics such as speed and flow. And here is one example of that. Here you can see that in the road network, there are a bunch of loop detector which is spread over the network, which are basically collecting this traffic metrics such as speed and flow. Now, given those metrics, can we given those traffic metrics, for example, from 8 a.m. to 9 a.m., can you accurately predict the next 1 hour, for example, 9 a.m. to 10 a.m.? That's basically our problem. So here was the major challenge of doing that is the first and foremost is here I'm giving an example. Was the major challenge of modeling this kind of data in data-driven way is that, for example, here is a sensor and here is another sensor. These two blue sensors are placed on a highway which is going towards the city, and this red sensor is placed on another highway which is coming from the city. Now, if you see that those red and blue two sensors are very close to each other, but they are not actually, they are close in Euclidean distance, but they are not very close actually, because if you wanna drive from this blue location to red location, you may have to like travel and take a U-turn and come back to this. So the driving distance between these two is not small, like this is quite large, but they are located very nearby in Euclidean space. So, but we want to. So if you see the time series of these two sensors, you can see like the blue time series is showing the time series of this two sensor, and the red one is this one. So the time series also is very different. Now we want to map this one in our machine learning model. So we want to map this connectivity in our model. So that's one challenge, and so this is called like non-Euclidean spatial geometry, this kind of geometry. So we wanna map this we wanna model this in our data-driven model. The second is the time series. The time series also is non-stationary. So given both of these challenges, what can be a very good representation of this kind of data? So here we found that graph can be a very good representation of this data, because we can model these two sensors as two nodes of a graph, and this connecting edge is basically the driving distance between two locations. So for example, here if this two location is the driving distance between two locations is too far, then the connecting edge will be having a large weight. And if the driving distance between this two location is small, then we can connect that too with a edge with very low weight. So with this kind of representation, we are able to represent what is there actual in the data. So here I worked on a model named diffusion convolution recurrent neural network, which basically perform the diffusion convolution operation on graph, and there is one recurrent neural network which captured the time series data. Now I'll be talking about the diffusion convolution process a bit, which is basically depict the natural diffusion process on a traffic network. So here, this is a visual example what the network is doing basically. So for example, if you consider that this is the point where congestion happened at a particular time step t, and then in t plus 1 is going to be diffused in the nearby node. So here you see like the traffic is diffused in all the connected nearby node, and in the next time step is going to be diffused over the next nearby node. So that is how basically in this network the traffic is getting diffused in the network. So that's why we call it diffusion convolution recurrent neural network. And here is a simple equation of doing that, which is showing basically this is the adjacency matrix, which is basically the graph, and this is the degree matrix, and k is the number of diffusion step. This is basically then how many times it is getting diffused in the nearby node. So the process which I showed here is showing like that is diffused through maybe k times. So here this is s to the power k is the degree matrix. And theta 1, theta 2 are level parameter of this network, and x is the input. So we are summing that up for k up to k diffusion step. So that is how it's capturing the real scenario of traffic in this data-driven network, and this is the complete picture of this forecasting. Okay. So here, this network is taking the graph as the adjacency matrix and the time series data, and then the encoder is basically encoding the data in a and encoding the data, and then is passing to the decoder, and decoder is again decoding it, and then forecasting the future traffic. And inside each cell of this neural network, the diffusion convolution process, which I explained earlier, this is happening, and that is how it's capturing the natural traffic behavior and forecasting. So what we did is that we performed this diffusion convolution process to forecast the traffic of the entire California network, which is available in Caltrans dataset. So for that, what we did that we partitioned the network into multiple subgraphs and then performed diffusion convolution operation in each partition. Here the basic assumption was that the traffic in the northern part of California doesn't impact the traffic in the southern part of California. So we can, because traffic is mostly local in nature, that's why we divided that entire graph into multiple subgraphs and perform graph partitioning approach to perform modeling on the entire network. So this is basically to scale this operation for our whole California network, which was having 11K sensor location and 1 year of data. And now what we saw is that after doing the partitioning, this is actually, let me explain the graph. This plot first. This is the mean absolute error for 60-minute forecast, and this is the number of partition. And here we saw that so we started with 4 partition and went up to 128 partition, and we saw that as the number of partition is growing, the mean absolute error of the forecasting of 11K sensor is going down up to 2.2 mile per hour, and then it started growing up. So we found that basically this graph partitioning based approach helped to get better performance. So the 64 partition gave us the best performance here. And the most exciting thing is that the execution time. So in case of 64 partition, where we got the best result, the training time is reduced by 3 hours almost. So we were able to train the model in that way for the entire California network in just 3 hours. So that's really exciting. So because of this graph partitioning approach, we reduced the training time from here to here. Next, I'm going to talk a little bit about the transfer learning aspect, because sometime we had 1 year of data for the entire California network of 11K sensor location for 1 year, but that may not be the case every time. So sometime it may happen that we have a very limited new training data set for some location, we have large training data set for some locations. So can we transfer the knowledge from data rich region to data limited data region? So for that, we also worked on transfer learning, where we designed a network which is able to do this case. So here is the example. So here you can see LA and SFO, these are 2 regions. For example, if we have, so we did the experiment on LA and SFO, and we took the large data set, the training data set from LA region, and tried to forecast in the SFO region. And for that, what we did is that we divided the source subgraph into multiple source graph into multiple smaller subgraph. And this smaller subgraph, we trained this smaller subgraph one after another in the model. In each epoch, the model was taking all of the subgraph and performing the diffusion convolution operation. And by this way, it was basically learning the information which are not very specific to a particular location, because this was performing diffusion convolution of the subgraph one after another. So when when all the subgraph it trained in one epoch, that time it was basically not learned the information which is specific to a particular region, but instead of that it learns the connectivity and traffic pattern, the network in general from all this subgraph. So that is how the model basically learned the traffic network and the pattern from this subgraph. And once the model is trained, we tried some subgraph from the target region and perform forecasting. And we saw that this procedure gives us very good accuracy compared to those normal network which was not specifically meant for transfer learning. So these are to work in the spatial temporal domain, and so this is a glimpse of the work which I do at Argonne. If you are, so I want to, and this work has been supported by Department of Energy and Berkeley Technology Office of DOE. And thank you for attending the session. If you want to contact me, you can email me or check out my webpage. If you are interested in this kind of work, you can look at those things in my GitHub as well. Any question if you have any?
Do we have any questions?
Yeah.
Okay. I'll just give you the mic so that you can hear.
I don't really have a strong background in machine learning, but I'm curious if you, so using this adjacency matrix, you're able to model areas, I don't know, say like a stoplight that's congested. And then, of course, the time at which it's congested until, I guess, when all the nodes have been cleared, say it's like 10 minutes. Are you guys able to look at, if you add another neighboring node, does this improve the time it takes for, I guess, the graph to diffuse?
So if I understanding the question correctly, so here in the graph we are basically trying to represent the location which is capturing the data, and the congestion pattern which you are saying is present in the time series data. So when we are considering one location, the time series, it has all the pattern of congested as well as non-congested time. So when the network is learning, during the process is basically learning these patterns from the data, and through that diffusion convolution process. So if you are introducing more sensor in the graph, then also it will be capturing all the same congestion pattern from the time series of that location too. So it's not that if you are not basically if it is not very dense, then also it has the capability of capturing the congestion from the time series data. But yeah, the spatial connectivity is always helpful to understand it better in terms of like if a nearby area is congested, that is gonna be passed to the location, the current location. So it's always better if you can get a high resolution representation, or I should say like as much sensor location as you have. If you integrate those in your model, that's gonna be the best. But the model will be able to learn the congestion pattern if it is not very dense, if it is sparse also. Does that answer your question?
Sorry, I guess maybe a better way of saying is, you train on some data. Say you have 5 sensors, right? So that means you have 5 nodes on your graph. Are you able to use this trained data set to maybe simulate what like 6 nodes would look like, and how that diffusion process would be?
So here, here we are not using this data set to simulate But here we are basically trying to forecast, given this location and location information and its connectivity and the time series data, we are trying to forecast what's going to happen next and how can we best represent this spatio-temporal data in the network. So if you want to do the simulation, so we do work on simulation also, but in that case we use travel demand kind of model for the simulation and looking at those things. So
Great, thank you. So up next we have Sean. He's a fellow IU student. He's a master's in quantum information science. He has a wonderful background, and just to plug the club a little bit more, we have this connection from Oregon, from actually Alex himself, who's working at Oregon this summer. He, once again, to reiterate this theme, he's just a music student and now going into a master's in quantum information science. So really, it's for everyone, and if you should get anything from it, if you're from any background or anything, hop in, it's a great time. So for surviving this 4-hour-long adventure, we welcome Sean. Thank you.
Hello. Oh my goodness. Hi, everybody. So I'm Sean, as you were just told. And so today I'm going to talk to you about something I'm kind of excited about. It's a game. It's a video game. And it kind of helped get me into grad school. So QuTE Blocks is a game like Minecraft that teaches you the fundamentals of quantum computing. And I thought that was really cool, so I wanted to come and share that with you and share my experience. So I hope you guys enjoy what I have to say. So what is it, really? Like I said, it's a game. And games have rules, and the better you learn the rules, the better you get along in the game. And it just so happens that this game and the rules are based on quantum mechanics and things pulled from quantum computation. Things like entanglement, superposition, measurement and collapse of a quantum state, and things like quantum teleportation, which everyone talks about, sci-fi. It's really not, but it's not what you think, I promise. But the biggest thing is that it really taught me to become familiar with the circuit model of quantum computing, which is kind of the lingua franca of quantum computation right now. But on top of all of these abstract physics concepts that people tend to struggle with because they seem kind of esoteric, it taught me to become familiar with Qiskit, which is the IBM SDK, or the software development kit that they put out so that way people could learn to participate in the active community of quantum computing. But what it really does, it allows you to build circuits in 3D. So it helps you really work on the mind-body connection that we find so important in science. That's why we have labs. Physics 1 lecture, Physics 1 lab. Bio 1 lecture, Bio 1 lab. It's important. That's why it's here, right? And so before I really get too deep into it, it's pretty simple, right? You go in there, use these blocks to build a circuit that will give you some kind of output, which would be the answer to your question. Now, my professors in the audience are probably glaring at me because I am glazing over so much, but that's okay for right now. What you do is you'll build these circuits, you'll get your output, and then you can take the code that these circuits represent and put them into the IBM quantum experience, and you get to see what these circuits look like in real time, as if you were sitting there coding them yourself, regardless of how much coding experience you have or don't have. When I started my quantum journey, I did not know how to code myself out of a paper bag. And now I barely know how to do that, but I'm doing some really cool stuff on the side. So I guess I should really show you guys what I'm talking about instead of just talking about it. put this back up here too. So right now we're in one of the escape rooms in QuTE Blocks. There are a couple different areas in the game that you can explore, but the escape rooms are super fun. And right here, we're going to talk about entanglement, how to create an entangled set of qubits. Now, this is pretty much considered the Hello World program of quantum computing, and for those who are uninitiated, that is one of the first pieces of code or programs that you learn to write when you start learning how to code. And so I thought it would be fitting to show you guys just how simple it actually is to do some of these things, regardless of how highfalutin the science may be. Oh my goodness. Okay, so, good. What do you do? What do you do? Hold it. Oh, you're wonderful. Thank you. So here we go. We're going to get an X gate, which is just equivalent to a NOT gate in classical computation, just inverses whatever the thing is. Okay, so we want 0, 0, 1, 1 with equal probability. So I think that means we should put a Hadamard gate right there. Okay, that looks about right. And then maybe put an X gate right there. Oh, I think we're getting close maybe. And, oh no, that was not what I want to do. Apologies folks, this was much more rehearsed than this. And we do that right there. Oh my goodness, thank you very much, that was wonderful. And so we go in here. Thank you very much, I appreciate the applause. And so we can go in here, we can. There it is. And we can go right back over here. As I said, the IBM Composer is fantastic. If you really want to get down on quantum computation, check it out. And we go up here. Ooh. And this is the code and the circuit for the thing that we just built in the game. This is directly applicable to quantum education and just, it's cool. You're doing science and playing video games, and I'm a huge nerd, and whenever you can combine those kinds of things, it allows people to do things that they didn't think that they could. For instance, my background is actually in biology. That's what my undergraduate did. All of the research that I did while I was there was in molecular stuff, so very wet lab science oriented. No physics background, no math background, and I am not a computer scientist. But I'm still standing here talking to you guys today about quantum computation, and I think that is super, super cool. And I am very fortunate for that opportunity. And it is not exclusively James Weaver's fault, but the ability for me to become familiar with such absurd concepts in such an easy manner was absolutely fantastic and crucial to me getting here today. As I said, this was an incredibly gentle introduction to some of these concepts. I remember the first time I opened my textbook last semester, I got scared. That's a very real thing. And it wasn't until I realized that I was already familiar with these things that it became less scary. And I think that's a big thing that stops people from learning something they think is scary. And I'm telling you right now, it's not that bad. Because as of today, I'm currently working on a project with some folks using VQE to simulate a theoretical carbon compound that we think might be a good candidate. So, I don't know how to express how grateful I am for something like this to put me into a position to do something like that. And so that's great, and that's really what I wanted to communicate to you guys today, is that education in general, especially quantum education in the coming years, is crucial. So, QuTE Blocks uses 3D blocks, I guess, to teach you the fundamentals of this crazy thing that we call quantum information. Which, taken from the abstract, is just one of the neatest inventions or concepts that you can do. Taking something abstract and making it digestible to a significant number of people who would never have been exposed to that kind of thing. It helps you understand the basics of quantum algorithms, which is an extensive area of research right now. And it's fun. It's fun and you learn, and there's no reason, if you're not interested, obviously, but there's no reason not to explore something that can be fun and educational, regardless of the content. And with that, I thank everybody here. I'm Sean. Thanks.
Thank you, Sean. Thank you, Sean. That was quite impressive. So I remember I asked you, what is the theme of today? What are we doing here? We're trying to communicate to you what Quantum Day is about. What is quantum? What is this new thing that's going to revolutionize the industry in the coming years? And where is it going to make an impact? And so far you have seen that it makes an impact in music, it makes an impact in physics, obviously, in chemistry, biology, computer science, any other field that you can name. And that's the point of Quantum Day. That's why we celebrate Quantum Day. I hope you got to learn a lot today. And remember when you asked a question, where are the mathematicians? Yeah. We have been here for 1 year. We have been sending them emails, not getting anything in response. I think there's a reason why they don't get Nobel Prizes. We give it a shot again next year, and we're continuously in talk with them. They're quite nice people. They're extremely talented and very intelligent, obviously. It's just that they don't respond to their emails. That's the problem. Okay. So we're going to wrap up Quantum Day with one final talk. I want to reintroduce you to Stefano. He has recovered quite well, and he's interested, and he wants to talk to you about all the field of quantum computing research, especially in theoretical physics that he has worked on. So, thank you, Stefano.
Thank you. Yeah, so it turns out that the mind might be willing, but sometimes the body isn't. Thankfully, there was a variety of drinks that was brought to me. I had a selection of energy drinks. I picked a green one, which seemed to be the appropriate color given the spiders on the picture. I ate some Butterfinger, which I had not had before, but really good, I have to say. Worked like a charm. I will speak slowly, but I should be able to communicate my excitement nonetheless. So as I said, I wrote a book with Bob QuTE about a different way to do quantum computing, to communicate quantum computing, to reason about quantum computations. And without going over it too slowly, but Bob QuTE is at Quantinuum. He's the chief scientist of Quantinuum. Quantinuum is a large integrated quantum computing company. They do both software and hardware now. There was a merger with an American company that had ion traps, so now they are an integrated company. And they are very big in the education space. They put a lot of effort in there. They decided to publish this book. They helped us publish, and now this is something that they go around and want to present to the world, and I'm here on their behalf. I am with the University of Oxford, as is Alex Kissinger, who's the author of the other big book, the LOL book. And this is, as I said earlier on, a very big area of research. Now, but what is it really? So you've seen various formalisms and you've seen Kiskit blocks in the previous presentation, and this is complementary to that. It's an equivalent. There is a translation from the quantum circuit formalism into these diagrams, so you can match the various parts But these diagrams do something more than quantum circuits. Quantum circuits are a recipe. They tell you how to create a quantum state. These diagrams are both a recipe and a way to reason about what's happening in the computation. So you can write down a circuit in these diagrams, but there is more flexibility with them. You can do more, you can reduce them, simplify them, and by simplifying them, you can try and understand what is going on in the computation. So, this is this is the ZX diagram, and this ZX diagram has some qubit coming in, some qubit coming out, and some initial state, which is prepared, a couple of entangling gates, and some measurement that is performed at the very end. This, so far, is nothing other than a translation of what a quantum circuit would be, but you can do, as I said, you can do something with this. You can take the diagram, and now you can start simplifying it to see what's happening in this particular computation. So you can, for example, take these two spiders. These are the basic building blocks of our formalism, and you can fuse them together. And the fusing takes two spiders of the same color, and if they touch, if there is a leg that connects them, you can imagine it as a virtual qubit that is mediating an interaction between these two parts of our circuit. Then you can take one of the two and you can fuse it with the other. So you can take the bit there with the two green spiders that it's an interaction between three qubits. It's a plus state that interacts with a part of a CNOT gate. And then there's a rule, which is called fusion, a graphical rule, that says that you can reduce your circuit a little. So now you have one fewer piece in there. You know that the plus state somehow interacted with one side of this CNOT gate, and something changed. Like there was some information was compacted. You have a bit fewer pieces in your circuit. And you can apply the same rule to the two red dots, and that's the red dot on the left with just one leg coming out. That is a zero state. So anything which just says the wires carry qubits, they may be the physical qubits that the quantum circuits have, so they may be the qubits in your machine, or they may be virtual qubits. I don't know if you're familiar with Feynman diagrams, you may have heard of them, you may have seen them. In Feynman diagrams, there are real particles that sort of fly in space and you can interact with them, but their interaction is also mediated by a particle. But these particles are not really existing, they're virtual, they're called virtual, they exist for very little. But nonetheless, you can think of these particles as particles, you can reason them as particles, and they carry information, which is the important part. There is information being exchanged. So those, you can really think each wire is carrying one qubit worth of information, and it's mediating some interaction between the various parts of the diagram. Some of them correspond to the qubit being acted upon in time, so you can think of time going left to right. Some of them are just virtual qubits that mediate the interactions. But the calculus doesn't care about that. There's no difference. The calculus is just about the information and how the information changes. So you can take the zero state and make it interact with the other side of a CX or a CNOT gate. And the same thing happens. You can just fuse it. So there's a rule that says you can fuse these blobs of color. When they touch and they're the same color, you can just collapse them together. And you can repeat this for various parts of the circuit. You can do it on the other side. And this is interesting because so in the quantum circuit formalism, you have a state, and the state is acted upon by gates. And then you measure the state, and you get something classical, you get a bit. And there's a direction of time in this process that goes state, gates, measurement, classical information. This circuit doesn't care about time. You can really think of a measurement as a state coming from the future. As an information perspective, that's what it is. It's just you don't know which state. You have no control over whether you get the plus state or the minus state coming back. That's the two outcomes of a X-basis measurement. But you can put a variable there, like that B0. It's going to be a bit that represents the outcome of the measurement. You have no control over that variable. You don't know what will come out, but it's one of the two values. And now, from the point of view of ZX diagrams, that behaves the same way as the state. It's the mirror image of what happened on the left. We can just fuse to the right, and we discover that measuring in this case, measuring in the X basis, interacts in a certain way with the control of CNOT. And it interacts in a way which absorbs an angle, a phase, into that blob. So you have a CNOT gate, it has a control side, you have a measurement. What you realize in this calculus is that what happens by performing that kind of measurement is that you create a rotation, effectively. It's called gate teleportation. It's the basis of measurement-based quantum computing, for example. But as far as the calculus is concerned, you don't have to know anything about MBTC, you don't know anything about Hilbert spaces, you don't have to know anything about stabilizer formulas. All you have to remember is a small set of graphical rules that tell you how the information flows. We can apply the same to the second measurement and fuse again, and now we have a much simpler circuit. It's effectively a line, right? You can look at the information, it enters from the left, it goes through those blobs, there's some virtual qubits or physical qubits that mediate that information, and then it sort of continues at the bottom and exits on the right. So you can really think there is 1 qubit worth of information that flows through the circuit. What's interesting is that if you think of it as a computation, some of that flow goes back in time. You start at the top, go to the right, go back, and then there's that little bit there where you're going left. That's odd. Of course, it's not really that the qubit is going back in time, but the information in a certain sense is propagating backwards. That's what the diagram tells you. Now, really, it doesn't matter how I arrange these nodes on the piece of paper or on the screen. All that matters is how they're connected, is the flow of these qubits through the diagram. So I can, yank things. And there is an equation, if you will. It's a very trivial equation. It's a geometric equation. If you want to know how to get mathematicians into these talks next year, just tell them that this is category theory, or that this is higher topology. There's a bunch of names. I can give you some interesting names, there's the syleptic model categories that are involved. That's a recipe that we tested for years that gets mathematicians interested in this stuff. So that's the trick. So look at that band. That band is, it's just a line really, so I can straighten it to see more clearly what's going on. And now it's quite clear that there is a qubit coming in and going through a bunch of operations. Those are gates, and then the qubit comes out somehow affected. So the question is, affected how? I want to know what this computation does. I want to know what the effect of that initial circuit was. So I can look at those dots and think, oh, maybe I can simplify them. Maybe there are some more rules I can apply. And the empty dot with no angle is just identity. These are rotations. These particular dots here are just rotations in the z or x basis. The empty one is identity, so I can remove it. The identity does nothing. And that is a graphical, you can think of it as the identity does nothing, it makes sense, or you can think of it as a graphical rule. It's a graphical rule that says that whenever you have one wire coming in, one wire going out, and a dot with no angle, you can replace it with just a flat wire. And we apply that, and the circuit becomes simpler. And we look at the next one. Again, dot, no angle, remove, there's nothing. And then we look at these two dots. These two dots are again the same color, they touch. They have triangles, so we fuse them. Now, something that we didn't see before, both of these have an angle on them. The rule for fusion in general says whatever angles you have, you add them. So it's some form of rotation composition, if you will, and indeed we'll see that that's exactly what's happening here. So you have triangles, you add them, you get 2b1 pi, and the beauty about that is that 2 pi is equal to 0 as an angle. We're working on a circle. So we can really say, okay, well, that's just, it's 2 pi times something that is certainly 0. So we can replace it with this dot that has an angle on it. Now we know that that dot is just a wire, removed, repeat the game. Same color, they touch, add the angles, 2 pi, 0, done. There's nothing left. Excellent. And in fact, that was the point. This is the teleportation circuit. So what you've just proven, and this is a formal proof, by the way, it's a verification of the protocol. This is maths. As I said, mathematicians can be convinced to come to these things. That says that whatever we started with, that protocol that involves some plus state, 0 state, couple of CNOTs, couple measurements, some corrections, that all it was doing was taking the state of the qubit at the top left and copying it without error on the qubit at the bottom right. And we've done this, we've proven this by taking a slightly broader formalism that allows us all the necessary modifications to not only write recipes, but also reason about recipes, transform recipes into equivalent recipes. For example, this is used very heavily in quantum circuit optimization, because you have this intermediate representation that is more flexible. So you take a quantum circuit that you want to optimize, you convert it to a ZX diagram, apply a bunch of rules, automatically, of course, not by hand, and then you try to synthesize the circuit back. And that is extremely effective. In fact, some of the best simplification techniques for Clifford plus T circuits come from this. That's what brought this calculus into the mainstream. That's why it became interesting to quantum industry, because you can actually do things that couldn't be done before. What are the ingredients? Just to be a bit more formal, let's say. I gave you an example, I worked through it, I mentioned a lot of the rules, but I didn't really say what the pieces are. And the ingredients are just spiders. We call them spiders because they're little blobs of color. They have some legs coming in, some legs going out. They can be 1, 2, 0 on either side. They have an angle or a phase, if you will. When it's 0, we omit it, because why write 0 when you can just not write anything? And they come in two flavors. They are Z spiders and X spiders. These spiders are traditionally colored green. X spiders are traditionally colored red. The reason for this color choice is because when Bob QuTE and Ross Duncan originally formulated this, several years ago, Bob's office only had green and red pens on his whiteboard. So, the green went to Z, the X went to X, and the X went to red, and they've kept that ever since. But you can pick anything you want, the color doesn't really matter. You can do white and shaded, you can do white and notes with a cross, which is similar to the Qiskit composer notation. It's just a graphical device to distinguish them. I said that this fusion operation is kind of rotation composition. I mean, if you do two rotations about the same axis, the angles just add up. And indeed, if you take the special spiders, which just have one leg coming in and one leg going out, so they consume a qubit and return a qubit. They take a qubit in input and give one qubit in output. And what they are, really, is just rotations about the z-axis of the Bloch sphere and about the x-axis of the Bloch sphere. And if you compose two of these rotations, what you get are two spiders of the same color, with one leg in between. And the fusion rule, in this special case, says that you can merge them and just add the angles. And that's the same as saying that if I first do a rotation by alpha and then a rotation by beta about the same axis, then that's the same as doing a single rotation by alpha plus beta. So this is a special case of the fusion rule, but it motivates the fusion rule. But because we're working with such a flexible item, such a flexible ingredient, we can also think about states. There are special spiders that represent states on the Bloch sphere. For example, we can say, I don't know, maybe we come up with it by convention, and it turns out that it's a good convention, or maybe we reason a bit about what these spiders are. We say that the green spider with just one leg coming out, that has nothing coming into it and produces a qubit worth of information. So that is a state. It's a state on the Bloch sphere. And we say, okay, the green spider is the plus state. We'll see why, it will make sense, but for now let's just say that I think green spider is the plus state, red spider is the zero state. Okay? So what's the first thing we can try to do? Well, we can try to apply rotation about these states. We say, okay, well, now if I apply rotation by alpha to this green spider, I get another green spider. Now the angle is alpha. So I say, okay, I identify the green spiders with just one leg coming out and some angle. Those are the states on the equator of the Bloch sphere. And the nice thing about this is that the rotations act naturally on them. Fusion tells you how rotations work on these states. So if you take a state at an angle alpha on the equator from plus, and you apply rotation by beta, then fusion tells you that what you get is the state at the angle alpha plus beta, which is exactly what you'd expect. So yeah, this rule makes sense. And similarly, you can do it for rotations about the x-axis. It's just a different equator. And typically, when we have a sphere, we orient it vertically and think the equator is a great circle at the center, in the middle. But really, every axis has an associated equator, so you can take the x-axis equator. And the red spider states are the ones on that equator. I took a right-handed convention, but you can take a left-handed one if you prefer. So, let's go back to the last thing that we saw in this in the original algorithm that I presented, which is the CNOT gate. So CNOT gate has two pieces. It's two spiders put together. There is a control qubit coming in and a target qubit coming in. The control qubit coming out, the target qubit coming out, and then there's a leg in the middle. And in quantum circuits, that leg signifies that there is some entanglement being created, but it's just a notational device. Here, that leg is part of the graph. That leg says there is a qubit that travels, a qubit worth of information that travels here that does the entanglement. So the entanglement really is mediated by 1 qubit worth of information. And there are gates where 1 qubit worth of information is not enough. Not every 2-qubit gate can be written with just 1 wire in between. Some of them require 2, some of them require 3. That's an interesting observation. We've seen this applied in various settings in the algorithm, and we can give names, and these are familiar names. So for example, on the left, bottom left of our teleportation circuit, there was a CNOT gate applied to these two spider states. One was the plus state, one was the 0 state. That is just a bad state. So this was a bad state being created. We've seen it before in the Qiskit blocks. It's the same recipe. And the mirror image of that, where we now have some uncertainty as to what the angle is. There's these 2 bits that tell us, okay, we don't know which one will happen, but it might be a 0, 0, 0, 0, 1, 1, 0, 1, 1. Those are the 4 possible outcomes of these 2 measurements, and that's a Bell measurement. So if you take a Bell state and just do a horizontal reflection, you get a Bell measurement. And this is a thing in the entire calculus. The calculus is symmetric about changing of colors, but it's also symmetric about horizontal reflection, and reflection just does adjoints. So it's very easy to transform gates into other gates, but just turning them around, rotating them, flipping them, changing colors. All of those are allowed operations. There's a lot of flexibility. And the calculus has a bunch of rules. One of them is fusion. Fusion is a very natural rule. It has to do with the spiders of the same color, but there are a few other rules. In fact, there are about 10 in some presentations of this calculus. I think 9 or 10 is the smallest set of rules you can have for this. And those 10 rules are enough to prove anything you might want to prove about qubits. They are complete, people say. Any equation that you can prove between matrices, complex matrices, or between complex vectors, using linear algebra formulas, can be proven just with these diagrammatic techniques. They are as expressive. But they also afford you more, a higher flexibility. Actually, I don't know. They give you a different perspective. They're not exponential in size. It's a different cut of the space, if you will. If you try to represent a state of 10 qubits with a vector that has 1,000 entries, if you try to represent a state of 10 qubits with this formula, it depends. It might have 10 nodes, it might have 100 nodes, it depends on the complexity of the circuit. So you pay a lesser price for some, you don't pay the same price for all states. Some states are easier, some states are harder. It's a tensor network if you're familiar with the notion. There are some additional rules. One of them says that you can copy some states, only some states. Of course, the no-cloning theorem says you cannot copy all of them, but you can definitely copy 0 and 1. You can copy plus and minus, and those are the rules that tell you that you can copy states. There's that spider with 1 leg coming in and 2 legs going out. That's what you'd expect for a copy map. A copy map takes 1 thing in and gives you 2 copies. And those rules say that if you plug either the 0 or pi red spider, which are the 0 or 1 states on the block sphere, then you get 2 copies of that. And similarly, you can just take the 2 colors, invert them, and you get an equivalent rule that says that you can copy the plus and minus state with this red dot. I forgot to say, if you have questions, there's an incentive to ask them. Because there are 4 copies of the book there, and if you ask an interesting question, you get one. So, just say, I forgot, but that was the point of having them there. And so with this copy rule, we can perhaps look a bit closer at this CNOT gate and prove that this is a CNOT gate. So I've told you this is a CNOT gate, but you kind of had to trust me. But you can use this reasoning. This is a reasoning tool, so you can do a proof. And the proof goes as follows. You take the CNOT, you plug either 0 or 1 on the control side, so the green side, and then you apply the copy rule. And the copy rule says that you get 2 copies of that state. So the control output is in the same state as the control input. Check. So it's a controlled gate of some kind. The last part is proving that what's happening on the target is a NOT gate when the bit is 1 and the identity when the bit is 0. That's just fusion. You take those two blobs, yes.
I have a book already, so this isn't for a book.
Okay.
But I've been puzzled with, like reading this, I've been puzzled with the, by the notation where you've got the angle going on the right there, you've got the angle going down.
That is a very good question. You would have gotten a book.
Yes. I should read the book and then I'll understand the answer.
Well, the answer is very simple. It doesn't really matter which direction the wires go.
Okay.
There is no inputs and outputs are a notational convenience because you want to match the quantum circuit formalism where there's a left side and a right side, so you want to differentiate. But from the point of view of the calculus itself, it's working with undirected graphs, so you can arrange it however it pleases you. And the rules always work. When you go to QuTRITs or QDITs, then there are some subtleties because the transpose doesn't work the same in the Z and X basis anymore. It's no longer real. The transpose matrix is no longer real. So you have to pick a basis, and there are some complications. But for qubits, no worries.
So I'm curious, how does the copy rule get rid of like, the green graphical identity, and why isn't there a wire connecting the new red identity to the existing one?
So in that rule, you don't have. If you look at the diagram as a whole, there are no wires coming in and 2 wires going out.
Right.
So the diagram that you get on the right has to also have no wires coming in and 2 wires going out.
Okay.
And now, anything in between, you are free to simplify it as you wish. The only things you have to keep are the inputs and outputs. Those you keep fixed, and everything else you can just replace. It's graph replacement.
Okay.
So you have a lot of freedom there. But once you have this, once you've done the copy, then all you have to do is fuse, and you get either a 0 rotation or a pi rotation, depending on whether the bit is 0 or pi. And the 0 rotation is the identity, and the pi rotation is the X gate, so this is truly a control X gate. But what's interesting is that because all of this holds with flipped colors, we learned something that we might not have known about this control NOT gate, something which the classical control NOT doesn't do, which is that the target affects the control. So if you have a classical control NOT, the control remains in the state that it was, and whatever the state in the target is doesn't really matter. So the state in the target changes, but the state in the control doesn't. If you have a quantum gate, any entangling gate turns out both sides can influence the other when they are in the right basis. So here, if we put the control, we take the control in any state whatsoever, and we put the target in the X basis, so plus or minus, then we can apply copy again and show that what happens is a controlled Z gate applied on the control side. So in a sense, the C0, you can think of it as having a control and a target side, but that's a bit, I don't know, that doesn't really communicate what's going on in full. It communicates what's going on the computational basis, on the Z basis, but not in general. I think, personally, I find it easier to think of it as it has a Z side and an X side. It's symmetric. It's just the basis is different. If you take the green side and you plug in a Z basis state, it acts as a control X. If you take the red side and plug in an X basis state, it acts as a control Z on the other side. And this is interesting. It's something that you get by just playing with the colors. You take an equation that you already know and say, okay, this must hold if I swap the colors. I swap the colors, I get a new equation. And maybe that tells me something new about the world. And then without going over time, just very briefly, there are a few rules. I said they don't all look the same. One of them is this leg chopping rule that says what happens if 2 spiders of different colors touch. If they touch with 1 leg, there is no problem. That's exactly what a C0 does. The thing is, if they touch with 2 legs or an even number of legs in general, then you can chop off the legs in pairs and they disappear. So it tells you if you have these two spiders and there are pairs of qubits that put them in communication, then what happens is there is trivial communication. The 2 sides cancel out in some sense. And this can be used, I'll give you the slides so you can do it, but it can be used to prove, for example, that the C0 is self-inverse. That's one of the simple proofs. I wouldn't go so far as to say that it's the hello world, of the ZX calculus, but close to the other world of the ZX calculus. And there's another rule which says that you can pop squares. Everything is nice and graphical and colorful. And you can use this to prove something which is very common in compilation for superconducting architectures especially. You can prove that if you want to implement a swap, but you can't move the qubits around because they're fixed in silicon and taking them out is not good. What you can do is instead do this alternating ladder of CNOTs. And now you can do the check mathematically on the basis states and prove that this works as a swap, or you can stare at them and think, oh look, there's a small square of alternating colors. Maybe I can pop it. I can pop it, and I get a swap out of it because the legs invert. And now I have two CNOTs which are in the right order to be cancelled out, and I am left with a swap, which is a two-step proof that you can synthesize a swap by an alternating sequence of CNOTs. And there's a few more rules, but I also wanted to say you can, sometimes it gets a bit unwieldy to have all of these spiders flying around. Once you start having 10, 15 of them, your eyes might deceive you. It's good to have something 2D, something geometrical, because a big part of our brain is dedicated to recognizing saber-toothed tigers. And now that we don't have saber-toothed tigers, we can put it to use for other things. But sometimes it's kind of annoying to write a green dot, red dot, green dot, all this pi over 2. If you're like me, I don't write nice. The pi is hard on itself. Putting the slash, writing small, it gets confusing. You'll make a mistake somewhere. Instead, you can say, oh, this is the Hadamard. So I define a new symbol. It doesn't change the calculus at all. It's just a convenience symbol. But now it makes it easier to write more complicated rules or more complicated results. For example, you can say, oh, if I have a pattern that's like 2 of these Hadamards, so it's a six spiders, then they cancel out. This is not a rule that you have to impose. You can derive that. You can prove it. I didn't, but it's a very straightforward thing. The other rule is the one that says, oh, actually, the 2 colors are symmetric in more ways than one, and the best way there to understand their symmetry is to just think that the Hadamard is a change of color matrix. You can think of it as a change of basis. The 2 colors correspond to the 2 bases, so it's a change of color. Yes?
So are all these rules used to prove the quantum entanglement theories using quantum, or are these more in terms of like quantum computing in general?
Anything.
Okay.
These are rules for qubits, but there are versions of this calculus that work for arbitrary dimensions. All of them are complete, so all of them can prove anything that you could prove with linear algebra. There are versions of this calculus that work with infinite dimensions. There are versions of this calculus that work with quantum fields. You can write Feynman diagrams in them. They require a bit of mathematical black magic, but other than that, they look the same. Then if you try to ask how do you demonstrate that there is a model for this, then yeah, you need some non-standard analysis. But other than that, they look exactly identical. So the diagrammatic part is the same. You can do traditional quantum mechanics with these things. As I said, you can write Feynman diagrams. I think I'll stop here, really. I had a few slides on the cluster state, but you can see them on your own. I'll give you the slides. But yes, I'll answer some questions. Please.
So when you say that there are 2 states and they fuse together and get an output, so
yeah,
we can see that.
Yeah.
So if given an output, is there any way to backtrack?
So the rules are symmetric. They are equations, but they are formal equations. So they are symmetric in the sense that you can always go back, but you did lose something applying the rule. You might have more rules than one that you can use to go back. So the question is, if I have the identity at the end of this circuit, if I have the right thing, sorry, where is it? There you go. If I have the right, it's just a wire. How do I come up with what's on the left? How do I synthesize it? There is no good way to do that. You have to imagine.
My question was like, if given a circuit, I can come up with this one, but if I get this one, how can I go back?
You can just apply the rules backwards. So there's a fusion rule. You can think of it as you fuse the spiders, but really it's an equation, so you can unfuse the spiders. You can cancel 2 Hadamards, or you can introduce a pair of Hadamards. You can change color red to green or green to red, and all of these rules go 2 ways. So there's never any loss of information there. But you need the strategy to come back. Yeah.
So with the application of every rule, do we lose some storage space?
So the graph itself does require some storage space. The rules don't really. Most of these rules are basic pattern matching. So you don't. There's no overhead there. It's constant overhead, and it's also constant time to apply the rules. To find where to apply the rules sometimes is not easy. To figure out what sequence of rules you need to use to go from A to B. So to translate one diagram to another diagram, that is, I want to say, very hard, and I'm pretty sure it is very hard. I somehow remember that it's not it's complexity-wise not an easy thing to do. For some fragments of this, there is a standard way to derive equalities, but not for everything. There wasn't one more question. Yeah, 1 second.
So this is X and Z based. So I'm curious, do you need to worry about like Y basis measurements, or how's that handled?
So you don't have to worry about that because Y basis measurements are, you can perform them by first doing a pi/2 rotation and then doing either an X or a Z basis measurement depending on what you want. So it's, for example, if you think of you're trying to measure in this axis, the Y axis, one way to do so is to do this rotation, which is a pi/2 rotation by X, measure in the Z axis. So you can do red pi/2 and then Z measurement, or you can do Z minus pi/2 and then next measurement. So the Y spiders are synthesized in terms of the X and Z spiders. In fact, you can define Y spiders if you want. Some works do define these blue spiders, which are then translated into combinations of the other ones. For convenience, sometimes it's good, yeah, to have all the Paulis on the same basis. Pun not intended.
Okay.
Yes.
I have a couple of questions. I mean, the first question is you were talking about generalizations to QuTEs or, higher dimensional things. I mean, of course, this calculus works, in the way you're doing because of, you are essentially choosing this complementary basis. But if you go to the QuTE case, do you need to, for example, work with the Schwinger basis or things like that, or is something else?
So for the QuTE case, you get when I say QuTE, it seems like there is a version of this calculus for each dimension, but that's not true. There's a version of this calculus for each group of a given number of elements, abelian group of a given number of elements. So you just pick the Fourier basis for a finite abelian group, and that defines the Z basis is going to be the basis where the group elements are the basis elements, and the Fourier basis is the basis where the group characters are the basis elements.
That's the Schwinger basis.
Yes.
Okay.
Yeah.
Okay, so that's the point. Let me ask the second question. That, you mentioned that it's a way of simplifying, when you compile your circuit.
Yeah.
But, suppose I have a quantum simulation, or I have whatever. In general, you're not going to write things in this basis, so you will have to translate everything to this basis to apply then this kind of optimization.
Yeah.
Is there something you can say, to simplify this compilation?
So I'm going to pick a very simple example, which is not in a different basis, but nonetheless doesn't necessarily look like it is in this basis. When you do Hamiltonian simulation, one of the techniques that people use is trotterization. So you chop it up into small parts, and you use gadgets that correspond exponentials of Pauli terms with some parameter. That's one of the ways to do it, of course. Now, those exponentials are really just some small combinations of these green and red spiders in a specific pattern. So you can prove, for example, that the ZZ exponentials, the ones using QuaWa, I picked QuaWa because it's a particularly simple translation, are those little gadgets there. I think I have a slide. No, I didn't include it directly, but if you look at those gadgets with a red spider connected to 3 legs, that's a ZZ rotation. So it's an entangling rotation. Now, if you add a Hadamard on one leg, you get like an XX or a ZX. If you add pi/2 rotations on the legs, you get XY. So actually, you can write all of the generators for arbitrary rotations in this way. If you do trotterization and trotterizing the Pauli basis for qubits, then this is easy to do. Now, for QuTEs, that is not as easy to do. It's because for qubits, it so happens, of course, that the Paulis are both unitaries and generators for the rotations that correspond to Hamiltonians. For QuTEs, that's no longer the case. And so there is a bit of a mismatch there, and that's an open area of research. Finding good diagrammatic ways to write these exponentials for arbitrary dimensions is something that people are still working on. Even for QuTE, it's still open.
So is there any code that, some software that can optimize?
Yeah, so a lot of these techniques have been implemented into this package, into this Python package called physics. Oh, I'm sorry, there's a label on top of it. Let me just move this. There you go. So it's called physics, written PyZX, and it allows you to write ZX diagrams, and there are a lot of heuristics and algorithms implemented in it to do exactly quantum circuit optimization, quantum circuit simplification, synthesis, T-gate reduction, anything that John van Wettering and Alex Kissinger, who are both extremely prolific authors, have been working on for the past 4 years, as being implemented in this. So it's quite rich. So that I think at the presently for open source, maybe it's fair to say there's that, and there's Ticket, which is the compiler by Continuum, which is also open source now. So Ticket also has a lot of circuit optimization techniques. So everything that researchers at Continuum, so Ross Duncan and all of his collaborators have been working on for the past, 5 years, is implemented in Ticket. That's how Continuum became this sort of big quantum software company. They took the ZX calculus very early on, integrated into a compiler, and built software sort of optimization and compilation things on top of that.
So but you have to, first you need to write everything in this particular basis. If you have your own code or whatever.
There is a standardized translation. So both physics and Ticket have small functions that take code from Penny Lane, code from Qiskit, code from other common frameworks to write circuits, and translates it into ZX for you, and then optimizes that translation. So the point is, how do you translate it back? And there is also fairly standard ways of translating certain ZX diagrams back into circuits. One of the very interesting observations that came a couple of years ago, maybe now 4 years ago, is that ZX diagrams correspond almost exactly to lattice surgery procedures. So these spiders, the 3-leg spiders which generate all of the other ones, are the splits, the rough and smooth splits and rough and smooth merges for surface code lattice surgery. So actually, if you have access to a machine that can run lattice surgery, then the ZX calculus gives you a fairly tight language to describe that operation. It doesn't know about how the patches have to be oriented, but you can enrich it to include that. But there's various, depending on what your hardware, your substrate is, there are various options. Of course.
Examples, or can you point to any of implementing or representing quantum logic, like phase or amplitude logic, for an oracle, that kind of thing, in the ZX?
So there's works that looked at how oracles are phrased in ZX, and it turns out there's a fairly standard construction for oracles that you can do. In fact, you can think of the oracle as some box that you, at the start at least, you don't care about what's inside. Just group a big diagram into this box, and then say, okay, there are some pieces outside of the box, and I can reason based on those only. And there's this paper by Jamie Vickery and Will Zhang from, I think, 2013 or 2014, I can give you the exact reference, where they show that actually a lot of these oracle-based algorithms, the way they work can be demonstrated. So there's a proof that they work that is based almost solely on looking at complementarity and using these square popping and leg chopping rules, because of the pattern, the way that you construct the oracle is really based on that. It's based on the fact that you can rotate stuff, fuse and fuse, and then you get these wires that can be chopped, and that's it. So the way that unitary oracles are written is ultimately derived from these split and merge maps. I can point you to the specific papers. Any more questions? I think there's one more book that can be given away, if anybody feels adventurous. If not, then I think I am. This was a lot quite a long talk. Thank you for all your questions. Thank you for having me. And since I'm the last one, I just wanted to thank the organizers for the entire day. It's been an absolute blast. Thank you, Adrian. Thanks everybody for hosting us, for having us. It was really exciting.
So thank you guys for coming. Thank you for being a part of Quantum Day. I hope you guys also join us on Quantum Day 2024. We plan to keep continuing this. Finally, two things before you go. All of this was possible because of Adrian German, and we wanted to provide you some sort of a monetary benefit for coming here. So please collect your Mother Bear's gift card on your way out. So we're going to do that there. Second thing, you have been here for almost 4 years and 4 hours. Yeah, it feels like it. Okay, you've been here for 4 hours. It's still sunny outside, so make sure you feel that. So when you go from a dark room towards the white or the light room, it feels weird. So